the use of the equation. Okay, this one I did not pull up the most updated one, but the answer is correct. Now, first of all, I think many of you are confused by this because the most updated one, but the answer is correct. Now, first of all, I think many of you are confused by this because I did not review all the math here. I assume you learned it before, but it's not too difficult, okay? First of all, what is the work function of the silicon? Remember that, let's say this is the vacuum level, this is the conduction band, this is valence band. The distance here is 4.05 eV, right? This one is something you need to know, you need to memorize, okay? Maybe put in your cheat sheet. And then the gap is what? About 1.1 eV, right? So the distance from top to bottom is about 5.15 eV. Okay, so this is something you need to have an idea about. Now, if it is N plus, it means your Fermi level is very close to the conduction band. So the work function will be 4.05 eV, right? Can someone tell me if it is P plus, what is the work function of the gate?
Band gap plus or just 5.
Function, if the Fermi level is not at conduction band or valence band, then there and the Fermi level, the distance is equal to kT over Q times log the doping 1e, whatever doping. For example, in this case, 1e17 divided by 1e10. Okay, this is something I assume you know. If you don't know, better put in your cheat sheet. kT over Q at room temperature is about 25 millivolt or 0.025. Or you can calculate yourself. But again, this is if you don't know neither, put in your cheat sheet. 0.025. And don't worry too much, right? If you can give me the right equation, just substitute problem. You don't lose too many. Just a substitution issue. You won't lose too many points. You need the right equation and right approach, right? So let's say in the midterm, you suddenly forgot what is kT over Q. The substrate, I forgot what it is, Q3. You say the substrate is p-type. So because it's p-type, then actually I know that the Fermi level must be closer to the valence band. This is EI, right? So I can calculate distance by using kT over Q log 17 divided by 10. But I still need to know what is the distance from this point to the vacuum. And this is given by the distance from conduction band to vacuum, and then plus half of the band gap. Then I get this. Okay, now make sure you understand. Ask now if you have a question. Don't wait. Don't worry, you just say, I assume it is some value, okay? But you need to know the equation, right? So if this is the substrate, I forgot what it is, Q3. You say the substrate is p-type. So because it's p-type, then actually I know that the Fermi level must be closer to the valence band. This is EI, right? So I can calculate distance by using kT over Q log 17the substrate, I forgot what it is. Q3. You say the substrate is p-type. So because it's p-type, then actually I know that the Fermi level must be closer to the valence band. This is EI. right? So I can calculate distance by using KT over Q log 17 divided by 10. But I still need to know what is the distance from this point to the vacuum. And this is given by the distance from conduction band to vacuum, and then plus half of the band gap. Then I get this. Okay, now make sure you understand. Ask now if you have a question. Don't wait. Is what I'm saying makes sense to you?
And do we keep the units of EB? Like you said, we have to convert it back to joules?
Yeah, or no, you don't have to convert. I just say that when you need to convert, be careful. Here, if you use EV, it's the easiest. Because when I say this is 25 millivolt, is in EV, it's not in joule. Okay, so you can directly add them together, becomes EV. So if you try to convert to joule, you need to convert back again later. So in terms of number, just put this as 25 amp or 0.025 in the calculation. Okay, so you should see some effect from this term usually. Did I answer your question? Anyone has question about how to do this? If no, right? So hope that you memorize this equation, then you get, what do you get? Now we try to get the flat band voltage, right? Because I'm talking about voltage, I say I divide by Q, but actually you don't have to do anything because this is in EV, divided by Q, just remove the E. So it is 5M 4.05 minus 5.03 becomes negative 0.98. Okay, this is the flat band voltage. And then we go back to our equation. VTH is 5ms plus 5F, right? This 5F is actually this one. You calculated already. This term is 5F, right? Because this term is talking about the distance between the EI and your Fermi level. So this is the 5F here. When we do inversion, we want to invert it by that amount, that much of amount, right? Remember? Right? If this is the gate, right? This is 5F, this is 5F, so you invert the whole thing by 2 5F. Okay, so the rest is just equation. Hope that you really know how to calculate capacitance. This is epsilon of oxide divided by the thickness of oxide minus 7. Because I'm using cm, minus 14 is in cm, right? If you use 10 to minus 12, then it's farad per meter. Then at the bottom, I need to use minus 9. Then they are the same. This gives me C ox. And then the inside, you just substitution, right? 2 epsilon silicon 11.7, and then I need to remember multiply this 1, and then the Q, and then the N, and then 2 times phi F. Then you get the VTH. Is that okay? Any questions? Is that okay? And the N, and then 2 times phi F, 0.7, and this gives us, first, this is 4, and then the meter, then CF. This is epsilon of oxide divided by the thickness of oxide, minus 7, because I'm using cm, minus 14 is in cm, right? If you use 10 to the minus 12, then it's farad per meter. Then at the bottom, I need to use minus 9. Then they are the same. This gives me C ox. And then the inside, you just substitution, right? 2 epsilon silicon 11.7, and then I need to remember multiply this 1, and then the Q, and then the N, and then 2 times phi F. Then you get the VTH. Is that okay? Any questions? Curve, right? Then this is NMOS. This is NMOS, right? Because the substrate is P-type. So first of all, if it's NMOS P-type, I'm going to have a shape like this. Remember, need to be something like this, right? In the past, many students like to draw something like this. This is not a series curve, okay? In the inversion, you go very sharp. Accumulation and depletion, you have a slope. Then you say this is the flat band, 0.98, negative 0.9. You did that before. This is the threshold voltage, 0.82. But because this is a poly gate, you have a depletion. It is N-type. Because it's N-type, we already just studied earlier. Right, because it's N-type. When I apply a positive bias, it's going to bend up. So I have depletion. Okay, so you need to realize this. So I have a gate depletion. And then I ask you whether when it has a source string, then you can have inversion. If not, this will just keep going down without source string. This is what we discussed in the last lecture. Okay, any questions on this?
Professor, I thought on the email I read it was supposed to be high frequency for the.
Yeah, high frequency. So at high frequency, if you don't have source string, you can never invert. If it's low frequency, you still have time to do inversion.
Okay.
Do that make sense? Because if you don't have source string, you cannot generate electron, right? So if it's low frequency, you have time to generate electron through this electron hole pair generation. Now you don't have, it's high frequency. You need. Then let's go to what is the Cmax and Cmin, right? In this particular case, it's not difficult. Cmax, I told you that is C ox. We just discussed now when we're talking about assignment 2. So it's nothing but just the epsilon. So this one actually, result is correct, but I missed one, negative 14, right? Epsilon OX divided by TOX, you get this. And Cmin is this one, right? It is just COX parallel C depletion. And C depletion, here I try to do it for you as a epsilon SI on top, 11.7 times this guy. And then the bottom is just the equation, the depletion width equation. Okay, and then you get this one. Now let's say you are very uncomfortable with all this substitution. Then how can you increase the chance to do well in the exam if you are nervous? Write down all your thought clearly, right? Like all this equation, and then even you substitute wrong, you won't lose too many points. Okay, don't jump directly to the answer. Then I cannot give you partial credit. Now then we say that there's a change of the we add the fixed charge. Fixed charge is what? It's just equal to Q over. So don't worry about this. What I posted is updated already. I did not modify again. This was the wrong thing when I first do it, right? So this result is the same. So if you have been reading my solution, no need to change what you learn. QF divided by C ox, right? But negative. This term is always negative. So I have a positive fixed charge. So I put 10 to the power 12, then times the Q divided by the C ox. Then I get the shift of the threshold voltage. So it becomes negative now. Okay. Any questions? So actually, it's already 45. I was negative ops, right? But negative. This term is always no need to change. I did not. It's just equal to Q over. So don't worry about this. What I posted is updated already. I did not modify again. This was the wrong thing when I first do it, right? So this. This result is the same. So if you have been reading my solution, no need to change what you learn. QF divided by C ops, right? But negative. This term is always negative. So I have a positive fixed charge. So I put 10 to the power 12, then times the Q divided by the C ops. Then I get the shift of the threshold voltage. So it becomes negative now. Okay. Any questions? So actually, it's already 45. I will still spend time to talk about assignment 4 and 5, right? But you feel free to leave. I will keep recording if you in rush. Okay. I just want to finish it. So if no question, right, then I go to the question 4. Question 4 asks us that what is the subthreshold slope for this condition? You just remember what we have been talking about. Subthreshold slope is 1 per C depression even C ops. All you need divided by C ops. All you need to do just write the equation correctly, right? And then subthreshold slope is what? KT over Q times log 10 times 1 plus N, right? This one is 60 millivolt per decade, right? You want to memorize this number. I'm sure that useful in your interview. If you forget about this, it's not good. Right? So times N, then it becomes this one. Right? Is this clear for this part? Or even the part of the interview. If you forget about this, it's not good. 3 millivolt off. You just remember what we have been talking about. Subthreshold slope is 1 per C depression even C ops. All you need divided by C ops. All you need to do just write the equation correctly, right? And then subthreshold slope is what? KT over Q times log 10 times 1 per N, right? This one is 60 millivolt per decade, right? You want to memorize this number. I'm sure that useful in your interview if you forget about it for this part. If this is failed and warning my device using my another very thick oxide, okay, same thickness, right? And then I have the I try to do this. I have this gate oxide here, and then this is the silicon, and then I have another very thick oxide. So because of it, the depletion, so-called depletion, is just equal to the silicon in parallel with the box. All right, let me read again. Silicon is 10 nanometer, box is 100. This is 10, this is 100. So this capacitance is very small. Try to compare. This is 3.34. Okay, sorry, yes. Actually turned out to be similar to this one, right? But remember that this one is nicely doped, right? This is much smaller than the B, right? I did not show the B one, right? And how do I get this? Just find out what is the C silicon. Can anyone tell me how I find C silicon? Quickly. How do I find the capacitance due to this fully depleted silicon?
Is it ES over TSI?
Very good, right? It's as simple as this, right? And same here, to find the C boss, it's just ESOI divided by 100 nanometer, right? So I get back to 0.13. You see, they're very similar. I forgot if I do this deliberately, how come they are so similar, right? So I don't need to scale by increasing the substrate doping. I go to SOI, I solve the problem. I can have a smaller scaling, but I don't need to increase the substrate doping. I don't have the subtraction slope problem. Finally, I say that, hey, what? Just look at A. We just say that, oh, there are some trap, okay? And the trap causing 20% extra of the COX, right? So with trap, we know that this is just add them together, right? You have an extra capacitance. It's not in parallel. They always make it worse. And we say it's 0.2%. So we add it. As a result, your subtraction slope is even worse, okay? Any questions? Now, finally, the body bias question is a little bit difficult, right? You need a lot of thinking, but not really. You just need to be very careful, right? So first, we use the equation we learned from the class. We know what is the delta VTH. We add the body bias, right? Then all you need to do, just plug in the right number, and then you add the body bias. You see that I shift by 0.811. And I think this one refer to question 3. Body bias, you see that I shift by 0.811. And I think this one refer to question 3, right? We just want to add one more graph. And then I also want to know the C depression. Depression width is larger. So how do you see this? It's due to this one. This is 2 phi F and then minus VBS, right? 2 volts body bias. As a result, I have a larger depression width. So C min is the same as before, but the CD is smaller, right? Remember just now we say that C min is equal to C ox parallel C depression. It's still the same here, C ox parallel C depression, but C depression is smaller. So that's why I have a smaller bias. Okay. Now don't worry about this. This one I drew it wrong at the beginning. So this one, forget about the blue line. The one you saw in the canvas is correct. So this one was the original curve. Now, because of body bias, I have a lower C min, I have a larger VTH, but at the I also turn on my camera if you want to see who I am. By listening to my voice, some of you might think that I'm a female. Somehow my voice also. Permittivity, why this is important. For example, for silicon dioxide, what is the permittivity? This is 3.9, right? You don't need to memorize, but if you are in the semiconductor industry, you should know this is 3.9 times 8.854 times 10 to the power negative 14 farad per cm, right? I think I'm right, the unit, but still put a question mark here. This one is the so-called epsilon zero. This is the vacuum permittivity. For different material, you have different effective permittivity, right? Just recall, what is capacitance? I don't know if you learn about this equation, but we need to learn it. You definitely need to memorize. Just tell me, if I have a larger permittivity, do I have a larger capacitance or smaller capacitance?
Larger.
Thank you. For vacuum, right, it is 1, right? 1 times this one. So this one usually call it relative permittivity, right? But anyway, I just put epsilon here. It's larger, so it goes to the denominator, the numerator. What if I have for a capacitor, right? This is a capacitor, and this is epsilon, and it has a thickness, right? If I have a thicker capacitor, thicker dielectric, do I have a smaller or larger capacitor?
Larger. Oh, smaller.
Smaller.
Right? I don't think you can always get it right, right? So thanks for answering, because I can get it wrong also. But I'm so familiar with this because my research is all about this. But why I want to ask this? Because by asking yourself, what is the relationship of a quantity to the basic quantity? You can write down the equation. You is calling to test you, hey, is there a constant in front of it? Think is the same. Although this is n, this is p. A lot of electron on the left, a lot of hole on the right. And then I put them together. What happened to the electron? Electron wants to go to the right, and the hole, you put these two gas move is diffusion. So if the electron diffuse away, what happened? I say I lose electron. I am depleter of electron. That's why it's a depletion region. Okay. Similarly, the hole goes from right to left. The hole, this region, this one, lose the hole, and then you say I'm depleter of the hole. Then, it is a depletion region. Is that clear? Any questions? But now go to, so that's what you have been telling me, right? You just say that, no current because electron go to the right. Now can you tell me again? I just say that the electron keep going to the right. Why do you say that there's no current? You actually is just mentioned, but can you repeat? Electron go to the right. Would it keep diffusing forever? Then I have electron just keep going, and then the whole n region depleter of electron. Would it do that forever?
No.
No, why?
Because the holes are going the other direction, so if they're recombining. So the electrons are combining with the holes, so there's going to be electric field that's going to build up in the depletion layer, and current can't go past unless there's a voltage that you apply.
When the electron goes to the right, because and what I'm going to say now is this. What we do is to solve the Poisson equation, right? I'm not going to show here because this is forever as the capacitor. So I put in the denominator, right? Do you still remember if I apply a very high bias, reverse bias to the junction, would the depletion width increase or decrease?
Increase.
Increase.
If it's negative, it increases. If it's positive, it decreases.
Well, device physics. It can be like her memory is so good, it's like this. Negative, positive bias, this one is going to go down, this one is going to go up, then the depletion is going to get wider and wider. So this is another insight. Right? So I guess she probably have the insight. She probably cannot remember the equation. No one can memorize that. Right? So if we apply negative bias, it will go, so this is like this. Maybe you cannot get it, but basically we have a built-in potential. And if you have a negative voltage, then this one becomes larger. Right? So this one will be on the top. And if you have negative bias, it will go, so this is like this. Maybe you cannot get it, but basically we have a built-in potential. And if you have a negative voltage, then this one becomes larger. Right? So this one will be on the top. And maybe you probably don't know, what if I increase the permittivity? Is the depletion width going to increase or decrease? The depletion width, you buy the chip, you get double the function. And that is a big deal, right? Now it can be double for so many times. Later he revise it to be double every 1.5 years. But up to now, the first one is like maybe 1,000 transistors or something. Becomes what? 0.7 micron. You make it smaller. Scale the depth. Broken, let me say again. This is the cross section of the transistor, right? And this is the gate. And if you try to look in 3D, it is something like this. This is L, the length, and this is the width. And this is just a resistor. So longer gate length, smaller current, right? Small. So I just give you, say, it is proportional to the voltage and inversely proportional to the doping. So what do we say about the voltage when we do the scaling? What do we say for the nut? The nut reduced by kappa, right? So it becomes becomes V divided by kappa. Voltage is the voltage you apply to your transistor. It was 5 volts, becomes 3.3 volts, becomes 1 volt. Okay. And then how about NA? He said that we should increase it 1 over kappa. Of course, the T is going to decrease, right? Because we try to make the linear dimension smaller, right? And how about for capacitor? It's going to be larger or smaller? Current is going to decrease. Why? Because we just prove it. See that? We just prove that current decreased by kappa. Okay? Because of this, you see that the delay, right? If you try to cancel them, am I right? Yeah. So you mean copper reduced by copper, so the power is reduced by copper square. Now you see that the point is, yeah, you put more transistor on the same chip, but the total power is still the same because you make them still. I'm going to turn on the recording feature. Although I turn on the recording, I really hope that you will come at the class because That is the most effective way of learning. Right? Some of you might think that by watching the video, you can fast forward, skip the article of the day, play it with 1.5x. But V divided by distance, I reduce the linear dimension and reduce the voltage proportionally, then I have the same electric field. Make the gate length very short, then the control is even worse because drain and source are so close, so I have a lot of leakage. So that's why we don't want to go too fast, right? So it's slow down, okay? But overall, this is something we keep scaling. This one is something I want you to memorize. It's called contact poly pitch. Sometimes it's called contactor gate pitch, CPP. Right? If you can say this in your interview, right, I hope that I'm right, then I think it will impress people. I don't think many people know about CPP in the scaling, right? It's not about the gate. So let's take a look in this transistor. This is the source. This is the drain, right? And then this is the gate. Gate here is not really drawing the transistor. It's just showing you the location. The gate is here, and this is L. As it to turn it on, it's exactly the same. But because now you have the gate, you use two fingers to squeeze the water hose, so you have very good control, make it on and off. And that is nowadays technology. So each of this is like a fin, right? The fin on the fish. So that's why you draw this green one are the so-called fin, and this vertical one are actually the source drain contact. Very early time, they cannot use implantation. They use diffusion. They add a critical thing, right? Let's do a better large T, right? I can keep large. Why I want to make the thickness T? Why I want to keep it large? Why don't I make it very small? What will happen if it is very small? Say again.
Tunneling.
Thank you. Reduce tunneling. Okay. Everything has a reason, right? And then for the rest, I won't emphasize too much. First, right, we have so-called silicide, again, just to reduce the resistivity. You let metal react with the silicon. Just know that you have silicide. Silicide is like default now, right? Halo extension, the extension, right? We instead of actually this paper has some problem. Actually, it is wrong. This one should be N+, this should be N+. So I think this book has some typo. You actually have a more nicely doped in this region. Why do we need that? We just to reduce hot carrier injection, right? We are not going to study. We will study a little bit in memory because we use hot carrier injection to do programming. But basically, this is to increase the reliability, right? Which is called HCI. Right? I hope that maybe you just, if you love device physics, just try to understand. Okay. Halo is just a doping to prevent punch through to avoid the leakage. So halo is to reduce the subthreshold leakage. I can tell you all this, we can go into detail, and that will be half semester of an advanced device class, right? But this is not the purpose here, okay? So, but I tell you all the critical thing, right? Graph. The power keep going up exponentially. And actually, this is very interesting. I went to grad school this year, and at that time, they were all talking about this power war problem. And what they show us the picture is that they can use the Pentium processor to cook the egg. They show that. And then they say a few years later, I don't know which point, it will be the rocket nozzle temperature, okay? And eventually, it will be the surface of the sun temperature or the sun surface temperature. If you keep scaling in this way, no way we can do that, right? So see what happened. Intel at this inflection point, which is called inflection point in the paper, they slow down the frequency. Oh, so what is power consumption, right? It's the frequency times the CV square. C is the total capacitance of your chip, right? V is the voltage swing, and frequency is how fast you operate. If you don't operate, yeah, no power consumption. This is the frequency. If frequency has to slow down, we cannot keep going. Then then that's a big deal. You cannot keep going. Then your transistor is not, your CPU is not improving. But no, right? It keep improving since 2000, 20 years. Keep releasing new stuff, right? A lot of business arm, right? Acquired by different company. Why? Because they just reduce the frequency at the same time. They add multi-core, use parallel processing. So this is an innovation in architecture. Okay. So you can see that the gate delay, yeah, it keep going down since 65 nanometer. But at the same time, we try to reduce the switching energy. Right? So overall, the energy delay is smaller. Right? So what do we care? Do not just think about the speed. Yeah, speed is important. Right? If you cannot deliver what you want, it's a useless product. But at the same time, when you compare to technology, you want to compare the energy delay. Because someone can claim that I have a very fast transistor, but it consumes a lot of energy. Is this a good CPU? Really depends. Maybe you really need this one, right? It's just like maybe in NBA in a team, someone may eat a lot, but he's so good, he always shoot 100% on target, right? And you do need him. You need to pay him a lot just because he needs a lot of energy to achieve the goal. But if not, if your goal is not to have 100% target rates, right, then maybe you don't need someone who eats so much, right? So energy delay product is important. So this is a key concept, energy delay. Don't just look at energy, you need to look at energy and also delay to compare technologies. Right? Another is memory war. What does it mean? You see that we have different type of memory, right? The CPU performance keep increasing, but the memory does not. And the worst things is what? Is the communication between your DRAM and your CPU. And that's why NVIDIA becomes so rich, because they produce GPU, right? One is that to do multiplication, another is trying to bring some memory very close to it so that they reduce the speed and also reduce the energy consumption. And as a result, their GPU will be very suitable for the machine learning. Right? So this is something we need to break. If you keep scaling your CPU, the LG, yeah, it's very fast, but you cannot communicate to the data. What's the point, right? It's just like you are very okay. So then we have a system or a band structure. What we are studying is this on the top. I have a silicon at the bottom, and then I have a silicon dioxide, and then I have a metal. Metal, the special thing about metal is that it doesn't have band gap. All the electrons are filled up to Fermi level. Okay, it will just fill up to here. But that won't change our conclusion, because what we care is about Fermi energy. You might have electron on the top, very few, but Fermi level is where your probability goes to 0.5. Okay, so you have a Fermi level for metal. Okay, this is the oxide. We're doing a vertical cut, right? So we see the right. This is so-called conduction band. Valence band is down at the bottom. We don't see it because we don't care that much in here. Okay, and then here we have silicon. We have the conduction band here, valence band here, right? So in valence band we have a lot of electrons. These are all electrons, right? But our Fermi level is at this level. Fermi level, I say that the chance you occupy here is 0.5. It doesn't mean you can, because this time we did not build any room between these two levels. This time the building is like this. I have a lot of room, but then I don't want probably to occupy here. But right. And now, enough and leave the metal. If once you leave metal and go to the vacuum without kinetic, what you can? It's just the vacuum level. This is the vacuum level. If you don't know what's vacuum level, just think about Einstein's experiment photoelectric. You want to shine a light to the metal, then the electron becomes energetic enough and leave the metal. If once you leave metal and go to the vacuum without kinetic energy, that is the level. It's just saying that how do I leave the semiconductor or how do I leave the metal? It is the energy that you need. I mean, not the energy. This is the destination when you leave the metal, and that is the vacuum level. So electron affinity is just equal to, let me call this E vacuum, right? It's just equal to E vacuum minus EC. So you see that electron affinity for the conduction band is different from the electron affinity. For the silicon, is different from the electron affinity for the oxide. Some material have even negative electron affinity, which is diamond, passive rated diamond. It means that if you put electron there, it will just leave. It will just inject because its energy is higher than the vacuum level. You just want to jump over the peak. Okay, so this is electron affinity. Right? What is band gap? Can someone tell me how do you calculate band gap?
It's energy difference between conduction and valence band.
Very good, thank you. I know maybe it's easy for you, but still hope that you can participate. EC minus EV. So band gap for the silicon is very small, 1.12 EV. For the oxide, it is about 9.1 EV. Wide, very wide. Okay. And what is Fermi level? It depends, right? It can be. Not depends, it's just EF, constant throughout everywhere in this case, okay? And then now we say what is work function. Work function is very important. It is just the Q phi m, this one. It's just equal to the vacuum level. This is the work function for the metal. How about work function for the silicon? Q phi s equal to E vacuum minus EF of silicon. This one, okay? Okay, at the diagram, is there any larger one is smaller? In principle, insulates into the conduction band or hole in the valence band, energy, correct? And then 0.5. Band gap is so large, the electron that can reach conduction band becomes less and less. That's why it becomes insulator. So oxide, of course, it is insulator, but it's just equal to very wide band gap semiconductor. There's no fundamental difference. Okay, of course, sometimes they are not crystal, however, they're amorphous. But it's difficult to say. But now, and then at 0 bias, you can have band bending. Think about the PN junction, right? Maybe I'll cover in the band. At 0 bias, red. Fermi level should be constant when it's 0 bias. It's not the conduction band. At 0 bias, you can have band bending. Think about the PN junction, right? Maybe I'll cover in the later. Yeah, right. Remember, for example, right? For example, think about this PN junction. I apply 0 bias. You all know how to draw the band diagram for PN junction. Is there bending in the conduction band? There is, but it is 0 bias. Why? Because this Fermi level is constant. It's all about constant. If you learn about chemistry, this is called chemical potential. Right? Last time we talked about drift and diffusion. Although you have an electric field there, but I also have chemical potential. That's why? Because this Fermi level is constant. It's all about constant. If you learn about chemistry, this is called chemical potential. Right? Last time we talked about drift and diffusion. Although you have an electric field there, but I also have a diffusion counteract it. The chemical potential are the same. Right? So at 0 bias, what is voltage? It's chemical potential or a battery making chemical reaction, right? So this is called chemical potential. This is the Fermi level has to be constant. Then there's another thing called flat band condition. Flat band is what? Now it's talking about the band itself, nothing to do with the Fermi level. Here we're talking about the silicon substrate has to be flat, no bending, horizontal. 0 bias doesn't mean that it's flat band. Do you see this PN junction? I have 0 bias, but it's not flat. Right? I can memorize. So you need to keep correcting yourself. This is a very important concept. 0 bias means constant. Then we just follow the equation. We remember that the transfer voltage becomes the original one minus QF divided by C ox. So you have a positive charge, you just shift everything to the left. If you have a negative charge, you shift everything parallel to the right. You either try to understand or memorize it. You have no choice. You need to know how to draw it for this class, right? But it's okay if you don't completely understand, but that might make in semiconductor, okay? If now I have an acceptor here.
Yeah.
This is different, right? So now tell me. You say it's empty or filled?
So in that case, the acceptor is
Band gap is from where to where?
Conduction band and valence band.
Thank you. From the conduction band to valence band, right? Okay, so I hope that you understand this. These are the basics, right? And then we talk about the Fermi Dirac distribution on the right, right? So here we show that at different temperature, right, you have different probability. Usually we see this graph, but last time I showed you this graph, I just wrote energy, and then this is the probability. Then you actually at the Fermi potential, you always have 0.5 of probability to occupy. Okay, any question about this Fermi energy? Fermi Dirac distribution, and this is the equation. Yeah, good to ask now, right? Any question, feel free to ask. Exponential, which is exponential, this is 1 over, right? Participate. Because as I say, in this class, I want to have an atmosphere to immerse you in all the terminology. Every slide looks complicated, but if we keep talking about the hand waving methodology, draw this methane capacity, right? Metal, how would the band look like? This is just to test how,
it will push up the
In other cases, this must be rises first, and when we are very good at that, we will suddenly, at the same time, we start accumulate electron. This is Na minus. Right? When your electron is so high, yes, you keep depleting, but eventually it is so high that the conduction band is below the Fermi level, and I have a lot of electron. And now, can this acceptor move still? This boron, can it move?
No.
No. So they still cannot contribute to current. But how about the electron? Can they move? They can, right? Now a channel is formed, and we call this inversion. Someone tell me why this is called inversion. This is called accumulation. What accumulates the whole? This is called depletion. Depletion of whole and electron. And this is called inversion. What does it mean?
So you start inverted.
And something that's a lot. Yes. First of all, you see that we have something called Q psi B, which is EI minus EF. Right? This is the original EI and EF, and it determines how much whole we basically need surface WD mass is just equal to the same equation we have been talking about. Maybe you forgot, but again, you know that is inversely proportional to Na, the doping, right? Is there's a 2, that's okay, you forget. It's proportional to the silicon charge, and then the potential is 2Q phi B. You see that? You're just saying that our surface is banded by that. Okay, here is Vg larger than Vth, so I bend more than that, right? So if it is just 2Q phi B, then it is bending by this, so that this one bend down, the distance here equals to the distance here. Okay, any questions?
So a WD is the width of the channel.
WD is the width of the depletion layer. We are looking vertically from the gate to the substrate, not the channel, right? So what we are cutting here is this. If this is the transistor, source, drain, and this is the gate, right? This is what we are cutting. We are cutting A dash. So this is A, this is A dash. Is that clear?
Yes, thanks.
Okay. Any questions?
I have a couple questions, Professor.
Yeah.
On the case where you could be the gate voltage was greater than the threshold voltage. You said that it became an N-type material, but drop in Ni because we're working with a P hole, but we changed Ni to N.
Why? Because we accumulate a lot of hole here, right? The Fermi level is below the valence band, right? A lot of hole, positive charge. How about this one? Is this? Let's go this one first. Top right. What is that? Depletion or inversion?
Depletion.
Depletion, right? Because the bending is not enough, so the Fermi level is still close to EI. We don't have hole and we don't have electron, right? And eventually the inversion is enough, right? The conduction band is very low. And feeling of this MOSFET, the most important is the band. This is to ground. This is Vg. CQ sensitivity that we have, right? So let's call again permittivity. We studied before when we talked about Poisson equation. They're all connected together, right? Permittivity of silicon dioxide 3.9. If you want to memorize, right? Of course, you still have the vacuum one, right? 8.8, right? Times in farad per cm. Okay, if 12, then it's farad per meter. So last night I know how to find the threshold voltage, isn't it? Right? Because if we want epsilon Si 2 phi b. Is this correct? But actually, this is the oxide. But when clear or confusion? I mean, this is important, right? I want you to be absolutely clear. Okay, if no more question. Now, the problem here is okay, if no more question. Now, the problem here is we have been saying that the phi m equal to phi s. So even at 0 bias, there's no bending. Okay, what if they are not the same? Then let's think about a p-n diode. Can you tell me what type of device is this? Is it n or p on the left? What is this? Left is n or p?
N.
N, thank you. Because the Fermi level is
Fermi
close to
level
the, yes, close to the conduction band. And the p is right. When you bring it together, definitely they don't have the same wave function, right? Think about this. This is the vacuum. So this is the wave function of p, right? And this is the wave function of n. What do we know? We know that if we bring them together at 0 bias, you will have something like this, right? So you also need to understand to do this easily for you, right? On the left, far away, it is still n. On the right, it is still p. The band has to be continuous. So here we have a depletion region. Okay, so that's okay. Now, they are not flat band. How can I make this guy flat band? Just use what I told you. What bias should I use to make it flat band? We can apply a bias, right? Should I apply positive or negative to the left in order to make it flat band?
Negative.
Negative, so that I can shift the Fermi level up. This is almost impossible in reality because you are going to get a lot of, so I don't draw here because I don't want to go to quasi-Fermi level yet. But you need to apply very large bias and you actually will burn your diode. It won't happen. But the main point here is that if I apply a negative bias or I actually apply phi word function of n minus word function of p, right? Word function of n is small, right? Word function of p is large, right? So this is a negative bias. I apply this, then I can make it flat band. So this is the idea. So for threshold voltage, what I can do is I apply a bias so that it is flat band, and then I continue to use this equation. Okay, so if it is not flat band, not the same, right? So let me call this one, right? Here, this word n is all they are not flat band. I need extra voltage to make it offset. But is that a difficult thing? No, because again, remember, this is just a capacitor. It's just saying that I need to support extra charge. Then in order to get into the 2 phi s condition, I just need to add additional voltage. So because of that, right, VTH will have to add another term, and you trust me, it's just negative Q interface trap or Q fixed charge divided by C ops. Again, Q divided by C is the extra voltage, right? And then we plus Q phi ms plus 2. That's usually what we call this one as the flat band voltage. You apply this bias, whether you have charge or not, whether you're, so this is what you have been seeing in your textbook in the past. It is flat band voltage plus 2 phi s plus QD divided by, and the word function will bend my structure. So I need to make them flat band first, and then I derive the voltage, I need to invert the channel. So with this knowledge, if I give you something new, for example, some device called depletion mode, some called enhancement mode, some junctionless device, will bend my structure. Okay, so I need to make them flat. First, and then I derive some device called depletion. VTH is. Would I have a lower or higher threshold voltage? I have positive charge here. You clear. If occupied by electron, means before you donate, right? Before you donate something, of course, that is your natural state, right? Before you donate something, so neutral. So tell me, after I donate the electron, what would it be? What type of state would it be? I was neutral before I donate an electron. Now I donate an electron. What type of state would I be? Positive or negative or neutral?
Positive.
Positive. Right. Similarly, like acceptor. Acceptor is just think of a selfish guy. Okay. They always just take away from people. Okay. So before you take something from someone else, it's neutral. Okay. Charge equals to 0 if you have nothing. Right. A selfish guy. Right. So this means before accepting an electron. Then negative or neutral?
Negative.
Negative. Right. So what determines a state can be occupied or empty? What determines a state is occupied or empty in semiconductor physics? Look at this. Look at this. It's the Fermi level. Whether your trap is above or below Fermi level. Okay. If you are below the Fermi level, is it occupied or okay? High. What someone else is neutral. Okay. Charge equals to 0 if you have nothing. Right? A selfish guy, right? So this means before accepting an electron. Then what if it is occupied? What charge is it going to be? Is it positive, negative, or neutral?
Negative.
determine a state can determine a state is occupied or empty in semiconductor physics. Look at this. Look at this. This is the Fermi level. Whether your trap is above or below Fermi level. Okay. If you are below the Fermi level, is it occupied or empty? When it is empty, it must be above Fermi level. Okay. When it is occupied, it means it is below Fermi level. Same for donor. When it is occupied, this is occupied. Okay. When it is below Fermi level. So confusing. When they can get occupied, it has to be below or above Fermi level. Right? Whether they accept a donor is given by someone else, you don't know. I'm going to tell you. You came from experiments or came from experiment. Okay. And you see because they occupy. And if occupy. Any questions? We are going to keep reviewing, but I hope that at least you try to understand as much as possible at this moment. It's okay? Right? This is not difficult, but you need to follow the whole logic. Otherwise, it's so difficult to memorize. Okay. Now, good. So now we have everything, right? We learn the basics. Now, again, I say you don't need to memorize any equation. You need to understand the reason behind, because this is not a class just for MOSFET. You're going to apply this intuition to all the novel device. If you don't have this intuition, it will be a big pain for you because you need to rederive every time for every new device. Now, something called CV curve. What is CV? Anyone know? What does CV stand for?
Capacitance voltage.
Thank you. Capacitance voltage curve. So what does it mean? If I have a transistor, N plus P, I am going to apply a voltage bias. And then, as I said, I'm going to switch the gate for this accumulation. Thank you. And then what is this? Depletion. And then inversion, right? Again, let's remind, what happened to accumulation? When I apply negative VG on the left, I accumulate a lot of hole here. So effectively, this is a conductive plate. So what capacitance do I get? It's just the capacitance due to the oxide, right? Because whenever I change the voltage a little bit, all the charge will go here. Remember what's capacitance? It's just dQ dV. I change the voltage a little bit, I measure how much more charge will go in. And since this charge, you see that they're only separating by the oxide thickness. So I expect that I will get Cox in this region for accumulation. Okay? Makes sense, right? Because you just look at this one. This is just the charge you put on the two sides of the metal. It just looks like I have two sides of the oxide. It just looks like I have a oxide as an insulator, and that is the capacitance. But when you start going into depletion region, what happens? When I change the bias, on the top here I add charge, but at the bottom I actually add the charge to the depletion region. Right? This part is changing. So effectively, I actually have a thick. I actually add it, right? Because you just look at this one. This is just the charge you put on the two sides of the metal. It just, and since this charge, you see that they're only separating by the oxide thickness. So I expect that I will get Cox in this region for accumulation. Okay, makes sense, right? Because it's just dQ dV. I change the voltage a little bit, I measure how much more charge will go in. And since this charge, you see that they're only separating by the oxide thickness. So I expect that I will get Cox in this region for accumulation. Okay, makes sense, right? Because you just look at this one. This is just the charge you put on the two sides of the metal. It just looks like I have two sides of the oxide. It just looks like I have a oxide as an insulator, and that is the capacitance. But when you start going into depletion region, what happens? When I change the bias, on the top here I add charge, but at the bottom I actually add the charge to the depletion region. Right? This part is changing. So effectively, I actually have a thicker insulator. And it keeps increase when I increase the gate voltage. Okay? But eventually, when I reach the threshold voltage, what happens? Now, when I increase the gate bias, I'm increasing this one, because this one, when I increase the gate voltage, it just looks like I have two sides of the oxide. It just looks like I have a oxide as an insulator, and that is of the Cox. The oxide thickness. So I expect that I will get Cox in this region for accumulation. Okay, makes sense, right? Because you just look at this one. This is just the charge you put on the two sides of the metal. It just looks like I have two sides of the oxide. It just looks like I have a oxide as an insulator, and that is the capacitance. But when you start going into depletion region, what happens? When I change the bias, on the top here I add charge, but at the bottom I actually add the charge to the depletion region. Right? This part is changing. So effectively, I actually have a thicker insulator. And it keeps increase when I increase the gate voltage. Okay? But eventually, when I reach the threshold voltage, what happens? Now, when I increase the gate bias, I'm increasing this one because this one is fixed, the depletion region is fixed. When I increase the voltage, I add more electron to here. So for the whole system, it looks like I still just have a capacitor separating the charge by Tox. So this one will go up, and this is the inversion. Right? Is that clear? Right? If you understand what we talked about before, then this probably is much clearer. But the problem is that clear? We actually have a thicker insulator, and it keep increase when I increase the gate voltage. Okay. But eventually, when I reach the threshold voltage, what happens? Now, when I increase the gate bias, I'm increasing this one because this one is fixed. The depletion region is fixed. When I increase the voltage, I add more electron to here. So for the whole system, it looks like I still just have a capacitor separating the charge by T ops. So this one will go up, and this is the inversion. Right? Is that clear? Right? If you understand what we talked about before, then this probably is much clearer. This as what's the meaning of a capacitor? Capacitor is just this dq dv. Please remember the accumulation. You put it just reach inversion, boom, it comes up. Back to C ops. EI, the distance. But the depletion width is more than that, yeah.
Okay.
Okay, now, so we learned about the CV curve, right? Now I want to ask you, what happens if I have fixed charge? So this is V, this is Vg, we know very well. Okay, I draw the CV curve, then it goes up, inversion, right? Now, what if I have a positive fixed charge? Meaning that this is the gate. So again, my connection has problem. My question is, this is the regular CV curve, not right? Now, what if I have some negative fixed charge here? Meaning I have some charge here. Negative, positive, or negative fixed charge. Do you know what will happen to this curve? Any idea?
Channel. You shift left and right.
Yeah, shift left or right, yes. So if I have a positive charge, is it going to shift left or right? Now think about, I just told you, it is going to change the threshold voltage, right? Remember? VTH becomes VTH minus QF divided by C ops. So if I have positive with fixed charge, what will happen to the curve? Shift left or right? It will shift left, right? Because this is just negative QF divided by C ops. So this is for positive, right? Again, as I said, right, this is just, we just discussed this. We say that when we include this fixed charge, we just have a constant shift of the threshold voltage. And it is the same for everything else because it just changed the initial condition of your system, okay? What if I have a negative fixed charge? What will happen? Shift left or right? Anyone? If I have negative charge, then QF is negative, so it's negative minus negative, right? So it's going to shift right. Any questions?
Yeah, what determines these positive and negative charges on those equations?
Charge are different. You are different. I already tell you that what if I have positive charge, and that depends on your transistor.
That's the only thing that it
By C ops. So left or right? Yes. Turn to this. This curve? Any idea?
Channel. You shift left and right.
Yeah, shift left or right, yes. So if I have a positive charge, is it going to shift left or right? Now think about, I just told you, it is going to change the threshold voltage, right? Remember? VTH becomes VTH minus QF divided by C ops. So if I have positive with fixed charge, what will happen to the curve? Shift left or right? It will shift left, right? Because this is just negative QF divided by C ops. So this is for positive, right? Again, as I said, right, this is just, we just discussed this. We say that when we include this fixed charge, we just have a constant shift of the threshold voltage. And it is the same for everything else because it just changed the initial condition of your system, okay? What if I have a negative fixed charge? What will happen? Shift left or right? Anyone? So, it's just what value?
Oh, okay.
Right, I give you the brief at the
Negative.
Mhm.
Could you explain that again and how that works?
Oh, I have not covered the trap yet. Curve is something like that. You apply the voltage across it, you get a straight line at the same level.
Yes, if instead of having a donor,
Right.
you would
Right? We say that, okay, fixed charge. Unluckily, this is the gate oxide. There are some traps in between the silicon and the silicon dioxide. If I try to draw the Venn diagram, maybe I should draw this first. Inversion have electrons. Okay, and let me tell you, for example, let's say this is acceptor trap. Okay, now you tell me, is this acceptor trap empty or filled?
Assuming that is above the EF, it should be empty.
Empty. Why do you say assume?
Because you drew the EG instead of the EF.
Okay, very good. So EG, what I'm talking about is just this is EG. This is actually EF. This 9 is EF, but I'm trying to say this is the gap. So now is it empty or filled? Just use your reasoning. Is it empty or filled?
Empty.
Huh? Say again.
Should be empty.
Empty. Because it's above the Fermi level, right? So what is the charge when acceptor is empty? Maybe you forgot, right? Try to think about that. Now I show you the table again.
Neutral.
Neutral, right? Acceptor, empty, neutral. So if it is neutral, is it going to affect my curve? If it is neutral, it's just as if it is not there, correct? You don't have charge, you're neutral. Yeah, the state is there, but it's not affecting anything. So when you draw the curve, they're just exactly the same. Okay? But now, let me look at a more higher voltage. Someone tell me, is this positive or negative gate bias?
Positive.
Positive. Now this might be in depletion or accumulation, but doesn't matter. The point is, the trap is still there. Now can you tell me, are the trap filled or empty?
Filled.
Someone say filled. Are they all filled?
50%.
Thank you. Those at the bottom are filled. Those on the top are empty. If you're empty, you are neutral. You have no effect. I can ignore you. Those are filled. Are they what? Negative or positive bias?
Negative.
Negative. I mean charge, not bias. Negative charge, right? So then it means that if this is just equivalent to have negative fixed charge. We already learned that. What happens if you have negative fixed charge? What happens to the curve? It shifts to the right, correct? So it means that when you go to a high bias, you actually shift this guy to here. But it has to be continuous. So this one is going to run in this way. So it's not parallel shift, right? It's a distorted shape, right? Not parallel. So indeed, this is one of the methods for people to figure out whether you have fixed charge or trap in the interface. Measure the CV curve by looking at the shift compared to ideal case or theoretical case. You know that what type of trap it is. Now I only give you acceptor. I don't have time to go to donor. You can do the same thing. For donor, you're going to distort to the left. Is that okay? Any questions? Now, besides this, there's also one more important feature. In reality, you will see the CV to become larger in some portion because you have the capacitance due to the trap capacitance. Right? A little bit difficult to explain, but how do we explain it? When your Fermi level, when EF crosses the trap, it needs to fill the trap, correct? When you cross it, you need to fill it. That is just equivalent to have extra capacitance. You see a bump, and this bump, but if your trap bump, any questions? But it gives a lot of information regarding they are not moving. How can we make them move? Apply electric field. But once you apply electric field, how do I know what the velocity is going to be? It's related by something called mobility. Okay, I hope that you understand this already. Mobility. Now, mobility is what then? If I plot this as the velocity, this as the electric field is volt per cm, right? Then let's measure the velocity of the electron in silicon. You see that it will go up. Well, higher electric field, move faster, good, but eventually it's saturated. This slope is mu. It's what you have to do with the mobility. But unfortunately, eventually it's saturated. So if I try to ask, what is the mobility at this very high electric field? This is very high, right? I need to actually take this load. The mobility reduce. It has higher to transfer the energy to the lattice to generate so-called phonon. It's just like that you are in a hall where you have all the people lined up very nicely. Now you want to go through the hall. This saturated mobility and electric field. So as a cartoon, then I'm going to draw it like this: electric field, velocity, it will go up and then saturate. And this is the mobility. And usually we call this saturation velocity. Okay. Why this matters? Now we are not going to derive the currents for MOSFET, and I assume you all know this, right? First of all, for long channel in the old time, the gate length is very long. The current in saturation equal to W on L mu C off divided by 2 VGS minus VT squared. What? So look at this. This is quadratic. If I increase my gate voltage, the current increase quadratically. So from 2 times gate voltage, 4 times gate current because of this 2. Okay, this is so-called long channel. Okay, and of course we also have this channel length modulation. Okay, but these are the old story. So why there's a saturation? Let me remind you. Right, when you have a high VD, you actually have the so-called pinch off. Right, essentially there's almost no electron there, and the electron travel very fast because the VG minus the channel potential here is smaller than VTH. But nowadays we don't care about this, right? We care about short channel. That is the transistor we are using nowadays. What is the equation? Do you remember I just told you velocity saturation? Now it is so short, right? This is short. And then we apply the gate bias. The drain bias. VD divided by LG is a large electric field. Then you have the velocity saturation. You actually cannot pull it faster. So because of this, you actually will form a layer of electron very thin here, and they are all traveling at saturation velocity. Is that okay? Right? Because the electric field is fast, right? If you're low, then it travels slower. Now the electric field is large, so you travel very fast. Then what is the current? Current, of course, proportional to the width. It's also proportional to the charge. But we know that it's traveling in saturation velocity already. That's it. Now, here, we actually need to use the mobility and electric field curve to derive. Probably you've seen that already, right? We're not deriving here. But here, I already know the velocity. I even don't need to know the electric field. I know the velocity. I know they're traveling in with saturation. Okay? That's why I can say this. Now, what is Q? Q is just the C ops times VG minus VTH, because we only care about the mobility, the mobile electron. We don't care about the depletion charge. And then minus VD set. VD set is the saturation, the voltage, make it just in saturation. This gives us the charge in this region. And then times V set. That is the new equation we need. Now you look at this. The gate, if I increase gate voltage by 2 times, what happened? The current also just increased by 2 times. Saturation, okay? That's why I can say this. Now, what is Q? Q is just the C ops times VG minus VTH, because we only care about the mobility, the mobile electron. We don't care about the depletion charge. And then minus VD set. VD set is the saturation, the voltage, make it just in saturation. This gives us the charge in this region. And then times V set. That is the new equation we need. And also just increased by 2 times, linear. So you see that the advantage of applying high gate voltage is diminished when with short channel. This is not good. And you also see that people will say, hey, I want to have something with large saturation velocity. Because in the past, I increased the VDS, the current will increase, but now I actually need to have a larger saturation velocity, and that depends on the material. Okay, maybe I talking too fast, a little bit messy here. Any questions? Want to clarify? Is that all clear to you?
Just to be clear, when you say saturation velocity, what is saturated?
Velocity is saturated. Look at this, running fast. Right. We have been talking about the conduction mechanism of on state. So for in the past, right, we all say, okay, before VTH, it is 0. And then after VTH, it conduct. This is after inversion. But how about before inversion? Does it mean that there's no conduction? No. Now, I want to do a Venn diagram along the channel. Source. To here. Come. Yeah, who think there's no current? Okay, Adam also think there's current. Okay, Adam, you think there's current or no current?
No current.
No current. It is no current that has higher energy than the barrier. So I will see something like this. This can be 0 volt VG. Yeah, remember here when you
levels, I push it up, and then automatically on the left side I go down.
Oh, okay. Yes, but you can do this here also if you want. Right now you say that you apply positive. It's telling us, now I put this in log scale. Do you see that? -2, -4, okay? That is the meaning of subtraction swing. S is delta VGS. Going on this for later. You have an infinite temperature. I need to subtract this. I forgot to write fermionic, because it depends on this fermionic emission. This term I forgot to write. Fermionic emission. Right? You need to emit across this barrier in order to conduct. And this is the equation. Okay? Let's ignore N for now. N is talking about the depletion capacitance divided by C ops. It's not ideal, but I will cover later. But the point is, you see that the subthreshold swing is proportional to the temperature. Can someone tell me why? Why higher temperature? I need to have, this is less steep. For high temperature, I need to have a larger voltage difference in order to increase my current.
Because your Fermi distribution also depends on temperature.
Very good. Because Fermi temperature is depend on temperature. If the temperature is at 0, think about that. This is very sharp. So even you increase the gate bias, there's no current, right? And it only has currents when this conduction band suddenly cross over the Fermi level. You have an infinite increase, right? You only need 0 voltage in order to increase the current by 10 times. And that's why this one depends on temperature. So nowadays, the important thing is HS. What is a good transistor? S, can you explain why? Although I draw it already.
I'm assuming that's what contributes to leakage?
Yes, because small s, it means that you can turn off easily, right? So if you have a small, it's small. Okay, so this is our first taste on subthreshold conversion. Like, we will continue because this is a very important topic, right? At the first class or second class, I already told you all the work we're doing. So this is our first taste on subthreshold conversion.
When you were applying positive bias to the gate and the drain, we had more current leakage, right?
Yes.
So if we just apply like a negative bias, wouldn't that help us reduce the leakage current
Good
in that case?
Good point. What does it mean in this graph? It means we want to have negative VG. We just keep going to here, right? This is negative. Do you see that? It does have lower leakage, 1E minus 14. So this is how people also now, if you take E224, we talk about that, they have some super off transistor, they actually just apply the negative bias to the gate. Then your leakage is very small. I apply, for example, 0.6 volt, I get. But it's not that simple. We're going to, do I answer your question?
Yes, Professor.
Okay, good. Now we talk about tunneling, right? But it will be easier if I just quickly review with you what is energy, potential, and momentum. This is not that difficult. What is the total of the potential energy, right? What is kinetic energy? Usually we write it in this way, P squared divided by 2m. P is the momentum, okay? Energy is 0 here, right? And then I have this barrier. When the ball reach above this guy, right? When you reach here, what happens? We say that is kinetic energy equals to total energy minus the potential. Is this okay? I think it's simple for you, right? Maybe any question? Divided by 2m equal to E minus V of x, which is E minus phi b. Not that difficult, right? Basically just saying that if I have the potential energy of phi b equal to, what if my energy is less than the barrier? Now my E is here. Transmission coefficient should be 2 divided by h bar. Okay? This one makes the momentum here. You don't have real momentum, right? So this is not the real momentum because you get negative momentum. What do you mean? If you own it, but the more you own, the less chance for you to go it, right? Although you're just telling them that, hey, the area. Why? Because it's e to the power negative something related. Understand what I'm talking about? So that when the proportional to they do the integration of the area increase, it means it is wider than your
Trouble.
right. Okay. Yeah, that is very interesting. Right? We can always think about that. Now let's talk about another important concept: ohmic and Schottky contact. Right? There are lots of confusion. Like, what is ohmic first of all? Ohmic contact. We're talking about contact, metal and silicon. Right? They have a contact. You need to connect them together. Source, drain contact. What happened? There's some contact called ohmic contact. If you apply voltage and current and you do the measurement, you get a straight line, and that's why it's called ohmic, because it follows. Why it's called ohmic? Anyone tell me?
It follows Ohm's law.
Very good. It follows Ohm's law. Ohm's law is linear. I equal to V over R. So forward and reverse, they are the same. What is here, right? And then I put a cathode here to another edge to the anode. Apply positive, pull or go down. It's go up, right? Negative. Then what do I get? I get something like this. Now I need the electron to go over here. Very large voltage. What if I heavily dope the silicon? When it is heavily doped, it means at 0 bias, because it's even in the conduction band. I think apply a negative bias, what will happen? Right, go through tunnel. Okay. And then we talk about the Schottky contact and ohmic contact, right? Remember the ohmic contact, right? When it is ohmic, it means that the curve is something like that. You apply the voltage across it, you get a straight line of current going through the origin. Okay. If you apply if it is a Schottky, what does it look like? In the forward bias, it is high, but in the reverse bias, it is low, because it's blocking you in one direction, right? But then we say in reality, right? Reality, we actually has the Schottky plus tunneling, and it gives you an ohmic contact. Because the tunneling allows electron to go through the Schottky barrier, like this. Right, this is a Schottky contact. The electron can tunnel through easily in this direction. This is reverse bias. Right, when it is so thin, then all you can tunnel, if you can tunnel, then you have a large current. Then it is just like ohmic. Is that okay for this part? And say apply negative to the P is the same as apply. So so this is N type, this is P type, correct? Now apply it to P. So what happened to the Fermi level if apply positive to P? Should the Fermi level on the right going up or down? If I apply positive to the P, apply positive to the right, should the Fermi level goes up or down? Voltage, what do you? Smaller barrier for electron. Same smaller barrier for hole, right? So then I will have current. Okay, so this is his. I keep asking. So yeah, I hope you all can memorize this, right? This is something help you save a lot of time when you analyze. So on the right it goes up, on the left it goes down. This is again relative, right? You can say. Is that right? As a result, we don't have so far. Eventually, you will have something called band-to-band tunneling. What does it mean? Assume it's any questions? So only this amount of electron can go through. Is that right? As a result, we don't have current. That is the rectifying effect, right? Rectifying of the PN junction, right? Theory. How do you move the negative Q or forward bias for this PN junction? Reverse. So it means this must be negative, this must be positive, right? And that is right. We just say that if you apply negative to here, you push it up, put it down, right? And we say there's no current. But when your field is so large, you keep applying very large bias. Eventually, you will have something called band-to-band tunneling. What does it mean? This is in the valence band. In valence band, you have hole, but the hole is what? Lack of electron. Valence band, you actually have a lot of electron everywhere, right? In valence band. How about for conduction band? Conduction band, you actually have a lot of hole everywhere because you don't have the electron. When you don't have the electron, it means you have a lot of hole, right? Just like the water. You fill up the water, then you have electron everywhere. That is hole. But can it go to the other side? This electron, your energy need to as high as this one in order to go through this barrier. Or you need to say, maybe I need to give enough energy for this electron to excite to here, and then I can go to the conduction band. But, right, let me draw here, it will be easy. We learn about tunneling. This is just a barrier. Electron can also tunnel to here, right? And this is, so the electron tunnel to here, good. But when the electron leave the valence band, what happened? What is left behind? When you sit on a chair and you left the chair to the, you actually, so this positive hole see this barrier, it will try to move to here. This negative electron see this electric field, it will try to go to here. So I have an electron current going to here because electron is, when you reverse bias your PN junction with very high voltage, there's no current, like here, a simplified picture, because I just don't have the energy to go through the barrier. But indeed, when you make the electric field very high, this layer is going to be thinner, right? So now I need to say this. When you make the electric field very high, this is, let me call this D. When the one student asks, right? It's large, you actually have zero tunneling distance. Increase. Then the current is going to increase. Okay? Why? Remember? Increase. Then the current is going to increase. Okay? Why? Of negative equation. We just want to know that there's something called band-to-band. Why it's called band-to-band? Can someone tell me why it's called band-to-band based on what I say? Because it tunnel from valence band to conduction band. Right? I have electron in the valence band, it tunnel to the conduction band. So you need a lot of math, right? Not the purpose of our class, but someone called Hertz, right? He derived in 1992. He gave this equation, which is very useful in simulation. So you can turn on band-to-band tunneling in your simulation if you want. You see that it depends on the electric field. Makes sense. At the same time, it depends on the band gap more. Another is the junction leakage. What is junction leakage? Junction leakage is talking about this PN junction, and it happens when you have this band-to-band, right? Let me remind you one more time. The three different leakage. Remember, N plus gate leak have a. Right, this is log scale, so there's no negative value. Anyone Everyone comfortable with this curve? Can someone tell me where is the subthreshold slope? Where is the threshold voltage? Is it here? Voltage, right? So how could it gradually? Distribution. Fermi Dirac distribution. You have less and less electron that can go through, right? This is source, this is drain, this is gate. I hope you are familiar with this. If not, I really urge you to study, right? Don't wait until the midterm. We are having more and more material coming in. Okay? Then you think that if I reduce, then I expect this to go down. It will go up. And so this experiment, you will find that that is not the case, unfortunately. Somehow and somewhere, indicate. Now this is not easy to understand. I'm going to tell you. I hope that you can follow. If you can follow the student, a device like this. What is the? And then VD volt to 0 volt to voltage. This is P. I also put this as 0 volt, right? And then VD has to be certain voltage, let's say 5 volts. And now I reduce VG. VG goes from, let's say, 5 volt to 0 volt to negative 5 volt, right? This is what I'm doing. Okay. Then I expect there will be less and less current. But what happened when VG is very negative? Now I'm going to remove this, right? Let's say VG to negative 5 volt. What happened? I'm going to do a cut line along this. This is a cut line, okay? So I need to draw the band diagram, right? So this band diagram is very important in our class. It is of the semiconductor, which is N-type. It's negative 5 volts. We're cutting along this direction.
Up.
Go up, thank you. So this will be very high, and this will be very low, okay? So if you draw the band diagram, you solve the Poisson equation, right? Then you will get something like this. And I need to exaggerate a little bit more. Maybe even more, right? I do not draw a very nice figure, but I need to show that now because this is negative 5 volts and this is 5 because this is the drain. Okay, this is the drain, N plus. Okay, do you see that? Now what will happen? Now do you see that this is bending so much, a very high electric field? You actually will end up in band-to-band tunneling again. The electron in this valence band will tunnel to here because this is at 5 volts. Then the electron will just go to 5 volts. Okay, after you tunnel, then you get a hole, right? The hole is in the valence band. So it will actually flow to the substrate. This is the substrate, which is at 0 volts. So as a result, it keeps generating electron to here and then hole to here. Because of this, maybe let me don't write here, otherwise you get confused. It's from this region. You have the hole go to here and then electron go to here. Then you form another current because again the same. Hole flow is just the current, so going to the substrate. Electron go to the drain is just like the drain supplying current to the substrate, right? Because just like here, electron go to the left, electron current go to the right because electron is negative charge. So you have a net current, and this is why you get giddo. If you have a larger negative bias, right? If Vg becomes more negative, then it means the band bending. This is the band bending here, is more. Then what does it mean? The E field will increase at this part, and then more band-to-band tunneling. Right? I should say this called BT-BT. People always call it BT-BT. So you'll actually have more leakage. Right? Now we have taught lots of equations, but I don't ask you to memorize. But basically, this is a 3D, it's the divergence. Right? So what does it mean? First of all, what is epsilon? Can someone tell me what is epsilon? Permittivity, right? Silicon, dx squared, epsilon, right? It's like MOS. But anyway, we put a positive gate bias here, right? So you pull down. So now can you tell me it is an inversion, accumulation, or depletion?
Accumulation.
Okay, someone say accumulation. Thanks for answering. But let's just look back to the curve. When we do MOS, we start with accumulation, depletion, and then inversion, right? Now we actually apply a positive bias. So it is in the inversion. But how do I see that? You see that the band is bended here. So actually, the Fermi level is here. So you get more electron, right? So at high bias, positive bias, you get positive charge on the gate. Then you have the depletion. What does it tell me in Poisson equation? dE dx equal to rho divided by epsilon. This one, dE dx equal to rho divided by epsilon. I know the rho already. Rho is the charge density, right? So how do I find E? E will be equal to integrate of rho divided by epsilon dx. All I need to do is just keep integrating here. Okay? Now, maybe you're not sure, this is like a delta function, right? In the delta function, when you do integration, when I go from here, 0 electric field. Once I hit here, because of the delta function, when I do integration, it jump up. Then I don't have charge here. The area is constant, correct? And then suddenly, I see this negative charge. It will go down. And then I continue to see negative charge. It reduces the area, right? Total area, because it's negative. It go down in a straight line because this is constant. And that is how you get the integration. This one, you see QM, right? See nothing. And this jump, you see negative QS, right? And here, you see negative QNA. That is how you do the integration. We're not doing that, right? There's a lot of math. As a human being, you know that is integration. You know that integration means times the area. You will be able to draw this curve. Once I hit this one, it goes up. I hit another delta charge, I go down, jump, and then I go down slowly because of the constant charge. Right, so here, this equation brings us from here to here. Any questions? Right, I will talk about intuition more than equation. Now at this stage, even you tell me you forgot this one, it is fine because you only need to remember you integrate the charge to get the electric field. Integrate the charge to get the electric field, memorize it. Or you differentiate the electric field to get the charge. Any questions? That active in asking question. I hope that is because you define dx equal to electric field, right? So here we try to set something for straight line integration, and suddenly you go, and let me call this b. You go down because you see, let me just call this a. Okay, and let me call this b. Now, then you reach here. You continue to integrate this region, but integrate slower because now the area increase lower. But it's a straight line, so you have a curve is second order. Here you see b. So you get the potential, right? But this potential is the real potential. You then need to multiply by -1 to get the band diagram, because band diagram is the negative of potential. So now do you see that this one straight line and then curve down, right? Going down. Here you see this one goes up straight line and then curve up. We have this discontinuity because of the band gap issue. But that is how you find out the potential of this shape. You get the, so there's a few steps, right? Let me say this is step 1. But I can just give you this initial charge profile and ask you to tell me what does the band diagram look like. The electric field to get the charge. Field from negative Q, it goes constant. Correct? And then suddenly I see this negative charge. It will go down. And then I continue to see negative charge. It reduces the area, right? Total area because it's negative. It goes down charge. Epsilon dx. All I need to do is just keep integrating here. Okay? Now, maybe you're not sure this is like a delta function. Right? In the delta function, when you do integration, when I go from here, 0 electric field. Once I hit here, because of the delta function, when I do integration, it jump up. Then I don't have charge here. The area is constant. Correct? And then suddenly, I see this negative charge. It will go down. And then I continue to see negative charge. It reduces the area, right? Total area because it's negative. It go down in a straight line because this is constant. And that is how you get the integration. This one, you see Qm, right? See nothing. And this jump, you see negative Qs, right? And here, you see negative Qna. That is how you do the integration. We're not doing that, right? There's a lot of math. But as a human being, you know that is integration. You know that integration means times the area. You will be able to draw this curve. Once I hit this one, it goes up. I hit another delta charge.
That third chart.
Times we integrate, but depends on what you normalize. We add something very interesting. Poisson equation, right? This whole term is talking about this one. Remember the Poisson equation is the divergence, right? You can, if you put epsilon into here, it is constant. You have divergence square psi, phi equal to negative rho, right? Here is this is the rho. Okay, but in depletion region, you only have Na. Oh, maybe you kind of forgot what kind of charge we have. What charge do we have in semiconductor? Can you tell me what type of thing is going to contribute to the charge? Electron density, correct? And what else? In a region, you can have electron, and you can also have what? Hole. But hole is positive, right? I start using the TCAT notation. P represents for hole concentration. What else do you have?
Fixed charges.
What charge?
Fixed,
fixed charge. Very good. Fixed charge. We have two types of fixed charge.
Yeah.
Okay, sorry. So I was asking someone say there are charges, right? At the same time, because it's NMOS, right? I assume there's negative Na or negative rho divided by epsilon equal to big, right? It's in 2D. You basically okay. Just a concept I want to remind. Is everyone okay with that? Just like here, we use Poisson.
Yes.
Okay. Is everyone okay with that? Just like here, we use Poisson equation to derive electron potential. But when you go to Venn diagram, you flip it. It means the electron want to go to this lower part, right? Want to come. So this is one thing, and why I have a few things keep doing this. And then now we want to know a few things. First of all, what is a drift current? Drift current is the current due to electric field. This one is easy to understand. You have an electric field, you drive me, right? So what is that? I equals to Q times the density times the velocity. And what is the velocity? Can someone tell me how you relate velocity to the electric field? We learned that last time.
Mobility times electric field.
Thank you. Is equal to mobility times electric field. Now tell me, what is mobility related to the potential? I'm sorry, what did I say? What is electric field related to potential? We just covered.
Negative gradient.
Negative gradient. Right? You see how this changed, right? Now there is one problem in my equation. Do you think my equation is correct? I equal to Q and V. Think about this. I have an electron going this part. Does the current go from left to right or right to left? The current go from right to left. What's wrong? I feel there's now 5 volts to this side. Right is 0. But velocity is mu times e. So if you have a lot of electron, very high density, and some of them this is low density fusion,
Professor.
right? The electron will go if gradient dV dx is negative. Then the current should go to the right. Sorry, let me fix it. I think I might do something wrong, okay? But let me introduce another component, right? This is still another is so-called diffusion current. It is due to the gradient of electron. Even you don't have electric field, it's due to the gradient of the carrier. Even if you don't have electric field, they will diffuse from somewhere. For example, if you have a lot of electron, very high density, and some of them this is low density, I will have a diffusion current, right? The electron will go there. Of course, then it is opposite. The electron diffusion current is going in this direction. Is that okay?
Go opposite of the.
But now I direction. I don't know why the sign is okay. It depends on of the electron. Right? Electron. I have a gradient is reducing, right? So this is negative. So that is correct because the current instead of current and current by unit area. Okay, so your current, you have a lot of current flowing. Which is in, just stop here. Thank you. Okay, so it's 4:30. Let's start the class. So this is lecture 7. I think you all have submitted your project 1 report. Thanks for working hard on that. And now let me just repeat what I mentioned right in the announcement. Although I discussed with every one of you on what to do next, but actually it's still give a lot of trouble when we try to understand the device. Any question? Something called Einstein relationship. Just now I say that I have a lot of electron here, very few electron here. Very less dense electron here. Can someone tell me again what happened when these two electron gas, they are brought together? Right. This is a silicon on insulator, right? If we have a single gate, it has this equation.
The area with the more electrons, so the more dense is gonna go move over to the less dense one.
So it means that okay, and now the electron keep diffusing to the right. It becomes this.
Okay.
Right? So what happened? As you said, a field will build in. Field. So say at we know n equal right. This n diagram, is it a constant or it can go up, go down? That's why.
Oh, okay.
Take that. Equal to D, right? In drift and defeat the drift. Everything already, right? So here we are trying to introduce something. Then what is the total current? Total current is equal to the drift current plus the diffusion current, correct? Right? It's just that when it's zero bias, there's no current. Drift and diffusion current are opposite to each other. Here, actually, I make a mistake. The conduction band is 2. It has to be this as this one. Qn mu dvxd dvdx. This is the drift current. Let's come back to here, right? This is the drift current. And then for diffusion current, it is Q dn dx. We can Einstein relationship here. There's you have a hole. What happened? Right? This is for electron. Whatever. Why do I say this is positive? I mean, I also use the wrong symbol. I should use dp. Will be now then finally, then I want to tell you another equation, the so-called continuity equation. You don't need to derive, but nothing to derive, right? It's just telling you how they solve the equation in TCAD. Basically, this is what it says. If I have a box, right, and then in this box, I have current going out, J, right? I can have current going out. They are leaving this box, and this is represented by so-called the divergence of the current density. Okay, so if you keep having something going out, you need to have a source, just like water. If you have a water keep going out everywhere, right? For example, if you look at this box, and if I have water going in, water going out, like this, you will find the divergence of J equal to 0. It means that there's no net molecule going in or leaving the box. Okay, but sometimes they can be non-zero. Why? Because you can have generation. How can you generate electron in a box? Any idea? This is a typo. Should be recombinant. This is generation. How do you generate something out of nowhere? How do you generate something? Anyone? How suddenly you create an electron? The keyword, what I'm looking for is you have energy, right? You create electron hole pair, a hole here. It means the threshold voltage keep reducing when the channel length reduces. That is interesting, right? If we go back to our previous derivation, this is the equation for the threshold voltage. If you remember, I hope you remember, this basically talking about the depletion charge, the fully depleted region divided the capacitance. This is the potential drop across the oxide. This is the surface potential. You need to bend the silicon so that it just starts inversion. That's why we have this, right? Does this equation tells us that the VTH is going to reduce when we reduce the length? Anyone? Can you see that from this equation? When the channel length reduces, the threshold voltage will reduce. Can you let me know, can you see or you cannot, based on this equation?
No.
No, right? I don't see that, right? So, but this derivation, why? Because we use 1D scenario. We assume the LG is very long. When it is very long, I can ignore this, but Poisson equation is not that. We need to solve the 2D, 3D. They have interaction with each other. So this is wrong, this one. This is only correct when LG is very long. Okay, so this is first thing. Threshold voltage reduce when the LG reduce. Another so-called short channel effect also want you to memorize. We talk about Gittel. They rhyme with each other. This is called Gittel, drain-induced barrier lowering. It's telling you that the threshold voltage is going to reduce when the drain voltage increase. The drain induce some lowering on the barrier. Again, from this equation, I don't see that my threshold voltage should depend on the drain voltage, but it does. Okay, so there are two such things. So on these figures, right, we're trying to show that a long channel, because of this depletion layer due to this drain, you actually encroach into the channel. You help the inversion. Remember, we need to have depletion under the channel first, and then we have inversion. But now I don't have to totally rely on VG. Someone that doing extra for you. You were very happy. You try to control the channel, right? Transistor is that you control the channel using the gate voltage. You want to have the absolute power. Gate, you are the controller. Someone trying to infringe, right? Trying to steal away your power. Even you don't try to deplete it through this PN junction. So I don't need to add too much of depletion charge in order to get into inversion now because of this drain. Well, if this one is very, very long, I don't care about this one. I just like I'm the king, I'm very powerful. I don't care. You try to control what I'm controlling. But when the channel has become so short, right? Or maybe you are the country far, far away. I don't care. You try to control. But now you become my neighbor. You try to control my citizen. And at the same time, you see this depletion width memorize this threshold voltage roll off or the threshold voltage. And
equation for the VT, for the threshold voltage.
am I going to what? Sorry.
On the side,
There are a lot of equations, but actually, we are going to cover with increase the leakage current. The circle one is at VT equal to 0.1. Very low bias. You see the threshold voltage is reducing. Okay, so this is the VT roll off, right? Low bias, it is reducing already. But in additional to that, when we have a short channel, when we go from 0.1 volt to 3 volt, we have another even larger roll off. And this is the dipole, drain induced barrier lowering, right? You see here at long channel, no roll off, right? It means when I go from 3 to 4, no roll off. At the same time, no dipole, right? For example, at 4 micron, I increase the voltage from 0.1 volt to 3 volt, nothing happens. Okay, and this is the same for the PMOS. Is this clear for you? Any questions? Right? Wait, maybe the best way is just say that ideally, right? If there's no short channel effect, what should I expect? I expect this. Right, this is no short channel effect. But now you see that it dropped off, okay? And this is another picture about dipole, right? Let's try just to understand a little bit more. This is in log scale. This is not log scale. Let's look at this. I have two sets of curves, right? Let's look at 2 micron first. 2 micron is reversed the same, right? This is the log scale. Comes this group. Long channel.
Yeah, but what is the graph that we're comparing the change? Is it the one that the first dotted line that connects to the 15 millivolts? Is the 15 millivolts the threshold voltage?
Yeah, so we compared the shift of the, maybe I should also say something. Maybe this is something you might not be very familiar. So if this is VG, this is ID, right? In a linear something. You might not be very familiar. And this is also approximately equal to VTH. Okay, so the shift of the curve is the delta VTH. Maybe I say delta will be better. Right, delta VTH. The shift of the curve is the delta VTH. So now I look at the long channel curve, I have this. Now I find that my 0.2 micron curve becomes this. So there is a shift like this one. And basically it is the change of the VTH.
Oh, I see it now.
Okay, great. So then this is the roll off due to the from long channel to short channel. And now I see an even larger shift when I increase to 3 volts. So this is due to the dipole.
Do you add the dipole and roll off for the total change?
Yeah, so this is just something you need to define very clearly. For example, when you communicate with circuit designer or when you write paper, right? You not actually, because there's no standard deviation of what is roll off, right? Some people may even say that the whole thing is roll off. But just in this class, I would like you to be clear that I want to say roll off is due to the geometric issue, right? We make it shorter, then you have a roll off. And dipole is due to the voltage. But outside, when you talk to people, they might just say that the whole thing is roll off. The most important thing is just you say it clearly. Do I add them together? Depend on the purpose. Yes, for some purpose, we care about the total change, then we just add them together. But it's all about what's your purpose. Okay? But because sometimes, but what is the reference? So make volt, maybe it will be smaller, right? Because this depends on the bias. We does it, Diego, make sense?
Yes,
okay, good. Now, in the last minute, let me just quickly tell you the first theory. How do we calculate the delta VT? What you have asked, right? So this is so-called charge sharing model. What they try to say is that because of this depletion, this one steal away some of the charge. These are the charge originally need to be supported by the gate, but now supported by the drain. So I have less charge that I need to support, right? Because remember what is VT? VT equals to QD divided by C ops plus 2 phi S. Now QD is less, right? So this was the original QD, right? It becomes QD less, right? So if I call this QD, right, this may be QD1, Q1, and this is Q2. So it is less, and then it is given by this equation. And that's how they find the change of the threshold voltage. Okay, so I will explain a little bit more next time, and then we'll go through a few theories on how to derive the model, and that is very important to guide the scaling. Okay, so I will stop here. Any questions?
Okay, thank you.
Thank you. Will be no current flowing through this oxide. Then you have a very good control of your device. Right? This is the gate. This is source. This is drain. Right? This is a silicon on insulator. Right? If we have a single gate, it has this equation. When you have a double gate, right, you see that you just reduce this by half because effectively the thickness is reduced by half. We also have quadruple gates. What does it mean? Then you need to think it in a 3-dimensional way. Right? This is source. This is drain, and then you have the gate 1, gate 2, and then surrounding it. So basically, it's reduced by 4. And this is the scaling length that we are talking about. Right. So if we can add more gates to it, we have a better gate control, then we can scale the transistor even smaller. But this is another theory. So now we know that, basically we know a few things, right? In order to scale the transistor, I want to reduce the TOS. I want to reduce the depletion width, right? How do I scale it? How do I reduce the TOS? make it smaller, right? How do I reduce the depletion width? You need to increase the substrate doping. Now go back to the old equation. Remember this? This is proportional to ND divided by QND, something, right? Proportional to something divided by QND, right? That's why I said that you need to memorize this. I mean, remember this relationship. But what is the problem of increasing the threshold voltage, increasing the doping, right? I increase ND, the depletion width will be smaller. But what's the problem? Higher threshold voltage, right? Because our threshold voltage depends on ND. Try to read the equation. More band-to-band tunneling, because now the PN junction is deeper. Worse subthreshold slope. We will talk about this a little bit later, but I also hint you that the subthreshold slope depends on N, which is 1 plus CD divided by C ox. And this one CD, the depletion capacitance increase when ND increase. So you have worse subthreshold slope. And you also have the so-called dopant fluctuation. So when people scale the transistor, they basically follow the Dennard's law. They make the WD smaller and smaller, increase the doping. But we cannot continue for bulk because of this problem. That's why people start using the so-called silicon on insulator and double has less. Right? So if you try to use geometry, you can come up with this equation. You find the drain is going to have some control on our gate, because when you have a very, but what is this?
It's due to the applied bias of the drain.
What, can you complete everything? Say everything. What due to the bias of the drain? What happens?
The VTH will lower as the drain voltage
increases. Okay, yeah. So here shows the example, right? You see that the at long channel is here too. When you go to shorter channel, for example, 0.2, right? The threshold voltage reduces. Okay, I can hear you talking. Then you have this VTH roll off, right? And if you increase the bias from 50 millivolt to 3 volts, you have even larger VTH change. No, this is the band have some control on, right? For example, from here to here, originally from here to here is 1 volt. The model, all this depletion charge under the gate are supported by the gate voltage. So you need to increase the gate voltage in order to form a full depletion layer. But now the drain already forms partially for me, and this is this area. Right? So if you try to use geometry, you can come up with this equation. You find that the change in the voltage is just the change of this delta dq divided by C ox. Okay, you just said, I need to think about this. It is just a tape. You want to turn it on, right? The tape, let's say the tape, in order to turn it on, you need to twist by 90 degrees, for example. But now someone, which is the drain, somehow help you to twist by, to turn it by 10 degrees already. All you need to do is just change it by 90 degrees. Then you say that this is the same with our intuition. No, almost zero. That means delta VT is almost zero. Delta is talking about the change of VT. We just say that. Right? So if I can make L much larger than the more inside, longer, VTU T ox. Okay? And actually it is also okay, and it also gives the wrong relationship. It looks like short channel effects goes down with 1 over L, but which is not true. Okay, but that is okay. The point is this is a simple model. Any question about this model? This is called charge sharing model, right? The drain help me to support some of the charge. I have less charge to support as a gate. It can help the VTH, right? I hope you remember. I have drawn this curve to you earlier. What happened when you increase the VG? The barrier becomes this edge up. But it tells us that the change of the barrier has this form, e to the power negative L divided by LOA. What does it mean? What happened if L is much larger than LOA? What happened to the term? What is phi mean when L is much larger than LOA?
reduced to A1.
Becomes A1. Because e to the negative, a big number, is 0, right? Then it means basically there's no VTH roll off. There's no VTH roll off in this case. Okay? But it's impossible, right, to make it very large. I mean, we can make it very large, but useless, right? So here, what is A1? What is LA0? This is the equation it is given. Still wrong. But it introduced a very important concept called scaling length. For a technology, if you want to be scalable, right, you want to have a L larger than, for example, L at least larger than 3 LOA. Because when it is larger than 3 LOA, it's e to the power minus 3. Then that gives you a small number. Okay, and then from here we can study. Can you tell me, you want, for a good technology, do you want a long scaling length or a short scaling length? Do you want LOA to be short or long in order to scale?
What is LOA again?
LOA is a constant given by this equation. And we say that when the channel length is larger than LOA, this term will be 0, then you have no threshold voltage roll off. So this term tells us the change of the threshold voltage. No short channel effect, right? If your length, let's say 1 micron, and LA is 0.1 micron, your length is much larger than the LOA, so you don't have short channel effect. Now, do you want to have a small or a large LOA for a good technology? First of all, do you want to have short channel effect?
No.
No, you don't want to have short channel effect. If you don't want to have short channel effect, should the gate length larger or smaller than LOA?
Larger.
Larger, very good, right? Then from absolute point of view, do you want LOA to be small or large?
Small.
Small, very good, right? Because if your, I kind of running out of space, sorry for that, right? Okay, my internet was not stable, right? But the point is you want to have a smaller LOA, right? You don't have short channel effect, okay? But what's the point here, right? LOA, yeah, you give me the equation. Then what insights can we get from here? I want to have small LOA. How can I achieve small LOA based on this equation? Can you tell me? How can I achieve small LOA? How can I make this one small? Someone tell me. Well, to make it small, I want WDM to be small. It means I want to have a very small depletion width. Wow, this is consistent to what we said earlier. We want to have a small depletion width compared to the gate length. What else? What else do we need to have a small LOA? A small depletion width compared to the gate length. From here, by the way. My internet had problem. Anyone? Can you hear me? Just let me know if you can hear me.
Yeah, we can hear you.
Okay, now you answer. Very good. Outside. You want it to be small or large?
You want it to be large.
This is a little bit confusing, right? You both have in the denominator and numerator, right? So let's assume that this term, the second term, can be ignored because outside usually smaller than the WDM. Then you actually want it to be small, right? So you're right, but it really depends which term dominates. But why do I need this equation? Well, you can put in cheat sheet, but the point is, this gives us the intuition. We need a small outside. Make the gate capacitance large. It makes sense because I want to control my device. I want to control it. So I make the capacitance large by reducing the T-ops. I also need to have less depletion because if I have smaller depletion width, just like here, I have less encroachment. I have less charge sharing. Is that okay? Any questions? If not, then let's go to the next page, right? Here, I try to show you the fitting of this polynomial potential model, which is the theory two, right? They solve the Poisson equation, assume the Poisson equation has a polynomial form. Eventually, they find out what is the reduction in the barrier, and they come up with, they introduce something called scaling length for the technology. And here shows the change of the pretty well, right? Of course, if they don't fit well, they don't submit the paper, right? Potential across the here is constant, but in reality, it is not. In reality, this is the electric field. If this is the outside, I have fringing. Just now we say that if we have T-ops, we want the T-ops, right? But I still want you when you study, go through this because then you understand how the importance of this channel length is, and tell me whether you want to make it small, right? Whether it makes sense, right? Whether it's counter your intuition or whatever. Is that the equation even longer? I don't bother to put in the slides. But the main point is this: they try to solve the Poisson equation. They find that it's changed. That is what we are talking about. But solving Poisson equal to 3.9. They just increase the outside thickness by 3 times. Not really 3 times. When they solve the equation by 11.7, thickness, the thickness, right, becomes T-ops times 11.7 divided by 3.9. Increase it according to this, and then we put the permittivity as 11.7. Here also put 11.7. This is not exactly correct, but they solve this and then they get this equation. The reason we make it larger is why? Because we want to keep the same capacitor. Remember, the capacitor is equal to epsilon divided by T-ops. By doing this, it is constant. We did not change the outside capacitance, right? Because I make it thicker and the dielectrical constant goes up also, then the capacitance is the same. And they come up with this. Now, the question is, does this make sense? Same as this, right? We want smaller LOG. This is the scaling length, right? Remember, the scaling length is that if your gate length is larger than the scaling length, then you can scale it without short channel effect. I have connection problem again. Let me say again. The scaling length is that when your gate length is larger than the scaling length, then you don't have short channel effect, right? Your gate length need to be larger than scaling length. So that's why you make the scaling length very small. Then you can keep scaling, right? If your scaling length is 1 nanometer, I can scale to 10 nanometer, 5 nanometer. If your scaling length is 1 micron, I cannot go lower than 1 micron because if it's lower than 1 micron, I have short channel effect. How can I make this make sense? Epsilon ops is to increase the, but this length need to be there. This increase is the I can give you another scaling length. We want the T. I have constant electric, and then so when you want to okay question. Also, myself by 11 here also cool to I made scaling value that the scale and also along with dielectric constant in the outside. We don't scale it like here, right? We don't scale. Also have to satisfy this equation, okay? And then we can plot them here on the right. On the right, we plot the depletion width. We scale it by scaling length. On the vertical axis, we plot by T-ops, scale by scaling length, and then each of these is a solution for different epsilon OX divided by epsilon SI. Any question about this plot, right? So maybe it's confusing. we solve the equation. Don't worry about how they solve it. They just tell us that eventually your scaling length, your T-off, your depletion width, your dielectric constants have to satisfy this equation. Right? Then you can solve it numerically, or we can just plot on a graph, right? So they plot you to the graph. Each of these 9 is a solution. For example, if your epsilon ops divided by epsilon silicon is 1/3, which is silicon over silicon, silicon dioxide on silicon, then you have this curve. This is the solution. It means that if your WD is here, then your T-ops is here. For example, 0.8 plus, so this is 11.7. This is just a silicon, okay? And then I have a gate oxide. It is 7.8. So this is not silicon dioxide. It is actually silicon nitride, okay? And then I say that the oxide thickness is 5 nanometer, okay? So this is the gate source drain, and the depletion width is 10 nanometer. Do you understand the question? Any problem about this question? And you want to find, question is, find the scaling length. Okay, how do you find the scaling length? Now I know that, first of all, right, I know that it will be on one of these curves, okay? And also I know already what is Ti divided by WB. 5.0 divided by 10.0 equals to 1/2, right? So this is Ti, this is WD. So it means what? It means I will have this load. So all the solution must lie on this point because the Ti divided by WD must be 1/2. That is one thing, right? Second thing is I need a curve that represents this ratio. This one is equal to 7.8 divided by 11.7 is about 2/3. This is 1/2, 1/3, this is 1. So the curve must be somewhere like this. Right? So this is the curve of epsilon I divided by epsilon Si equal to 7.8 divided by 11.7, 2/3. Okay, this curve, right? The intersection between this curve and this line. Is that okay?
Oh, yes.
Yeah, and from here, then I know what is WD. Short channel effect. But if I tell you that my process has a LOI of 10 nanometer, then you say, okay, let me draw 13 nanometer. I'm sure that there will be no short channel effect, and this is my typo. This is with no short channel effect. Make sense? Okay, my connection has problem again. So let me say again. This one refer to VTH roll off due to LG. And he introduced something very important called electrical integrity. Okay, so your final threshold voltage is just the original threshold voltage, means the LG equals to infinity. Subtract this 2 number. You give me all this quantity, I will know that. I will know the result. And it is easier to compare across technology. First, are you okay? Don't look at the equation first. Are you okay with what I'm saying? Why we have this? We have a new model. This model tells us how much threshold voltage change is due to VTH roll off and how much is due to the dipole. And how to calculate it is here. And they share the same something called EI, electrical integrity. This is important. We can use it to compare different technologies. When we say technology, it means, for example, planar versus SOI versus FinFET. Let's say 3D transistor. Okay. Now let's take a look. Integrity. What we try to do is this. This is a so-called bulk FinFET, bulk transistor. You have source here, you have the drain here. Correct, right? So let's write down what is the electrical integrity from the last line. EI times T off. LEL is of a dipole is small, so we want it to be small. Someone tell me, how can I make the EL small from this equation? Can you hear me? What else? How can I make EL small from the equation?
Oxide thickness.
Say again.
Oxide thickness. This is
Oxide thickness. What do you want to do with the oxide thickness?
decrease.
Decrease. What else?
Yeah, less junction depth.
Less junction depth. What else? Maybe you cannot see this of my right thing. What should we do? T depletion, reduce. Correct? And these are all we have been doing. This is correct, right? Make the channel length longer, then you don't have short channel effect. Make the gate oxide smaller, you have good gate control. Make the junction depth smaller. In principle, it means you increase the doping, you reduce the depletion width, right? Same, reduce the depletion width, right? So that is what we need to do. How can we do that? We actually can do this with other devices also. We're going into the details later, but now we can actually see some of them. Hey, this is the junction depth, right? And this is the depletion width. How can I make it small? I just inserted oxide here. Do you see that? I inserted oxide here. This is the junction depth now, smaller. This is the depletion width now, smaller. So this is even better in terms of say the junction depth by using this. Kept the depletion width by having an oxide blocking the depletion width. Right? Double gate, we make it symmetric. We reduce them into half. And then in turn, take the symmetric, right? If I do the symmetric wheel, then both the depletion width, this is T depletion, and the junction depth is reduced by as a comparison, but this is just this bench. Remember this? This is proportional to ND. If not, I show you something called International Roadmap of Device and System. You can download from the internet. Every year it publish, right? It tell you at each year how the transistors should scale, and you give a name of the node number: 10 nanometer, 7 nanometer, 5 nanometer, 3 nanometer. But the gate length is different. You see, 20 nanometer, 18 nanometer, and even later, you just keep constant 12, 12, 12 for all these technology nodes. But it's difficult. In 2020, this year, they publish a new one. You see that now they actually make the gate length longer for this 5 nanometer technology node, 20 and 18, right? This is high density, this is high performance. It's longer than one. Remember what is EI? Now then we say there are other theories also. Okay, this is again about the scaling length, because we are going to your interconnect is roots. Before we say when we make transistor, you try to change this phi s, right? You apply VG to modulate phi s. What does it mean? Look at the band diagram. This was the band diagram cutting from source to drain, right? When I apply the VG, this is phi s. What happened? Phi s reduced. That's what a transistor is about, right? I showed a few times. Any question about this picture? This is the central at the channel, and then the electron can go to see depletion. With depletion, I get that is higher than here can go through down. Am I right? Okay, that I want to EG1 increase this, but unfortunately, so you have a band-to-band tunneling increase, then the leakage curve. Does it mean that it does? So it has a lot of problem due to this doping, so-called dopant orientation, because it's so small now, right? Some of the grain are in this direction, some are in this direction, so they have different crystal orientation. As a result, you feel that, right? It's just like you have in a class, right? If you have equal number of male and female, then you have an overall effect, right? Now, if your class is large, 54 female versus 40 male, it's almost the same as they are very different. I have 55 female versus 45 male, and 45 male versus 45 female, 45 female versus 55 male. I can still tell people, oh, it's about 50%, 50-50. But when I'm small, 3 people, right? 3 females versus no male, or 3 male versus no female, the difference is only 3. It's even smaller than the first class I mentioned. But that is a big change. Now I say my class is purely female, and then my other class is purely male, right? So you have this variability, okay? And then why, if you have a higher doping, this Na, I mean N subscript A, substrate doping, because now in the past maybe I have 10 atoms, now I only have 1 atom. Isn't that plus minus 1 atom you have more effect? But no, is it because we're talking about the VT? When you only have 1 atom, your effect on VT is more. If you try the so plus minus 1 atom. You have more effect. But no, it's because we're talking about the VT. When you only have 1 atom, your effect on VT is more. So you don't contribute to the variation. So okay. How to convert it? And then eventually your delay will change. Your circuit change by more than 25%. You don't want that. Because already when it's solving, you can have the tunneling. The first thing is the so-called Fowler, somehow related to the area about your energy. Triangle, you have more area. With electric field, it becomes a triangle. I mean, rectangular, we have more area, right? Originally, it was rectangle, but when you apply the field, it becomes triangle. Area smaller, more tunneling. Well, but now they even not this. This was used in the flash memory for your device, not Fowler, no high tunneling. You use a lot in your memory, your thumb drive, right? Now we talk about direct tunneling because it's so thin. I even don't care about the field. It's just very thin, right? Very thin. Increase of if you have a polysilicon, you can tunnel one. Any questions about this? On this? If not, I show you something called International Roadmap of Device and System. You can name of paradigm, right? So that's why I want to talk about scaling. I spend a lot of time, but I think that is okay. We have plenty of time because actually now I'm thinking for your project report, because we have too many people. Maybe for the last 2 class, I will not ask you to present. I might ask you to record a video, right? A few minutes, and everyone look into that, and then we have those to continue to cover the materials. Okay. Any question about scaling now? Here are some appendix for 2-region model. No need to study, but if you are interested, I include for your information. No need to study, no need to study, no need to study, no need to study, no need to study. And then we will start talking about silicon on insulator. This is what you need to study. This is a new topic. Okay, so before I continue, any questions? Okay, let's start the class. It is 4:30, and this is lecture 10, D2. So today I will finish the SOI, and then if we have time, we'll go to FinFET, right? I still want to spend more time to go to the basics to make sure that you understand all the basics, so that you can do the assignment, right? The assignment 2 is due soon, but I think we cover most of them, right? Only one or two things that you need to learn from. Of this depletion layer, you get a capacitor, right? Depletion capacitance. So you have something like this, right? This is a very big capacitor, CD. Okay. So as I said, you don't need to memorize the equation, but we have been talking about this a few times. This capacitance is related to epsilon SI divided by T ops. Not T ops. Can someone tell me divided by what?
WD.
WD. But here we don't call it WD because this is not the depletion layer under the channel, right? This is WD. This is maybe let's just call it TD, the depletion width of the capacitor, right? If you try to derive it, you will get the equation we show here. Again, you don't need to memorize it, right? In the exam, I will show you, or you can always Google or go to Wikipedia. But not memorizing doesn't mean that you can ignore it. You always need to ask yourself, how is it related to different quantity? You see that, of course, if I have a larger difficulty wiring, results will increase the capacitance. Right? You reduce the shock channel effect, but you make your transistors lower. Who is going to buy it, right? So that is the problem, right? But with SOI, then the game is changed. I can actually keep increasing the substrate doping, but because I have this very oxide, right? Now I still have this gate, I still have this N plus, right? But I can make this very heavily doped. That's okay. But now I'm going to add a berry oxide to it. Okay, yeah, even you increase the doping, now my capacitance really depends on this capacitor that I'm drawing here. Is too wide, so it's difficult to see. Maybe it's better drawn like this. It really depends on what? Epsilon oxide divided by box, by the thickness of the berry layer, right? So now I have another extra parameter. Yeah, question? Someone has a question?
Professor, if you increase the substrate doping, how is the width change? Like, how does it decrease the TD?
Because the depletion width, right? Let's think about what is the depletion width. Do you remember? The depletion width is proportional to, right? Or even if I don't know if I remember the correctly, 2 epsilon SI, right? Built-in voltage minus VT divided by QNA. Do you remember this equation?
Yes, Professor.
Yeah. Now, so when you increase the NA, TD will reduce. Right?
Okay.
Yeah. So we cannot always go back to the equation, right? That's why this type of intuition is very important. When some people say that the doping is increased, you immediately remember that thickness is going to reduce. Okay, it is going to get worse. So yeah, so this one is like when you do this box in very outside, you introduce a variable for you to design the transistor. Originally, you need to increase the doping, but then at the same time you increase the capacitance. It's bad for your device. Now I can increase the doping without increasing the capacitance. Of course, it even decreased quite a lot because we have a thick berry oxide. Okay, and this is the equation. Like I'm not going to derive it. It's useless to derive this. Even this one is an approximation. Actually, it also considers the depletion under the berry oxide. So it's okay, right? No need to memorize, but you need to understand what's going on. And it's in the reference I quoted. Okay. Any question on this? Like even I need to look at the cheat sheet. Okay, let's continue to build the intuition, right? So now some of you already. Okay, let's continue to build the intuition, right? So now some of you already realize that, okay, yeah, you add the berry. Okay, let's continue to build the intuition, right? So now berry oxide, how should I burn SOI? So what the distance D? So something related to this, right? You have a bottom neutral. For enough put the if I make it where is the path size defined by copper actually, or is it? And there's an electric field. Just like a slope, you have a ball there, it's going to roll down, like gravitational field, right? DNP will be the same as DNPD, the neutral regions. But from the top, we can also look from the bottom, right? We just rotate ourselves, rotate the computer. Isn't that this is also a gate at the bottom, right? The only difference is just that, well, this one is very thick. And the second issue is that the interface quality might be worse, but it is still a gate, right? I can call this gate oxide semiconductor. I also can call this gate oxide semiconductor, and that's MOSFET. So actually, a fully depleted SOI is basically just a 2-terminal MOSFET. If you decided to use the back gate, right? You can say I don't want to use it, but if you try to use it, it can be 2 gates. So if it is 2 gates, then what does it mean? It means we are going to affect each other. I can turn this on by applying a high bias on the top. I also can. This looks like complicated, but I do negative VG. Then it bias to an MOS, very high positive. And now inverse the yeah. If I draw it, right? I try to apply 5 volts and 5 volts here. I pull it down. Then what happened? Both the remember, right? Accumulation. Other regions. Right? The first type is we spy. Share the same sub n plus well. Electrical or PN bias over bias. I make this one positive and PN you will have a good product. Okay. So for partial depleted SOI, I can just use body effect. However, for fully depleted SOI, I cannot do that because this is fully depleted. I'm not going to be able to influence the potential in a depletion region, right? So what can I do? Then I really need to use the backgate bias, right? So I have two gates. Now, math is complicated, right? I don't think our class will want to do that because after all these 5 pages long derivation are just approximation. They are actually, you can say, wrong, right? Although this is not. So if not clear, you can make. Okay, let's pause a little bit. Is this clear? Any questions?
Sorry, which lecture did we talk about backgate?
You mean the make the barrier lower, right? Why making barrier lower is good? Because region. Interview. What is a threshold slope?
By
Us. N, we call it N. It is not because just like what we say, I increase VG by 100 milliwatt. It only take 80% to the channel, right? It's like I said last time, like the government take the tax from you when you earn $100, right? So it's not effective. So this is because of the depletion. We did not really talk about the interface trap capacitance. We talked about interface trap capacitance in the earlier lecture, but we did not incorporate into this equation. But anyway, it is something that's hurting you because you need extra capacitance. You need to fill up the trap first because before you can bring up the potential or bring it down, right? So or large depletion capacitance for a good subthreshold slope. Like this. Here you say that in order to reduce the phi s by 80 millivolt, I need to increase the VG by 100 millivolt. Same here, asking how much VG1 I need to apply in order to get this change in the surface potential. Right? So this is just the inverse of this, right? Phi S1, phi VG1. How do we calculate this one? Like this is a little bit complicated, but it's not too difficult. Right? Basically, it is again a potential capacitive divider. Okay? So if you try to calculate it, right? I put only calculate the middle part. It will be C ox 1 then the gate oxide, correct? The bad side is in accumulation, then that is a different story. This is because now you actually, this part is grounded because it's in accumulation, right? Because phi S2 is grounded, right? So you cannot continue to enjoy the series effect of two capacitance, which make the N or the alpha small, right? Because it's no longer in series. Yeah, but CSI is going to be very thin, right? We have a very small CSI. So actually it's worse than the bulk. So that's why usually we operate the fully depleted SOI in this mode. We don't try to have accumulation at the backside of the SOI. Right? So these are some of the concept, right? When you calculate the silicon capacitance, you use epsilon I divided by TSI, right? And that is what you get for this one, right? So that's why this one has CSI, right? And this or alpha is just C, actually have very bad subthreshold slope. Similar to what we have done before, but I still show you. But to be frank, this is not that important equation because now it's velocity saturation, right? Last time I already showed you it is no longer in square, this is in linear. Okay? But just even usually the textbook don't talk about that, but I still put it here so you have an idea, right? Don't need to memorize it, but understand that for different type of device, right, you have different N. Now I want you to continue, but understand that for different type of device, right, you have different. Now then people say, okay, thin is good. Can I go to ultra thin? What they call the UTB SOI. Now then you will see something very interesting. The threshold voltage keep reducing when you reduce the thickness, but suddenly it increases when it is very thin. And that is because of the quantum confinement effect. If you look at the Venn diagram vertically, right, you have this box. So this is just a potential well. Because of potential well, you are going to have something shifted up. Right? Remember the particle in the box. You cannot gain the ground level. Your wave function can only stay in the first level, right? And so that's why you have this correction. So in your assignment, what I ask you to do is just plot. I actually forgot exactly what it is, but I ask you to plot maybe EC as a function of the threshold of the thickness. I would like you to understand when you make it very thin, you have this quantum confinement. As a result, your threshold voltage increases. And that's all I want. And you don't need to memorize the equation again, right? This is TSI. Okay. So I think that's it for today. I will stay for a few more minutes. If you have a question, otherwise you can leave now. Okay. Thank you.
Professor, I have a different question regarding the assignment.
Here we are not using SOI, so you actually have silicon. So we talk about du delta VTH.
Right. It's only pretty much VTH or EC divided by Q, right?
Yeah, if you want to get the number correct, yes, divided by Q. Q. Yes. This E0, but this is not EC0. This is already a new energy, right? You cannot have energy in between. So similarly, when you have the silicon on insulator, when it's so thin, this is the EC0, right? This is the EC0. But your energy, just like this one, right? So maybe I should use another color. This is the EC0, just like here. This is the ground energy. Classically, you are going to have this is wave function. You are going to have this energy.
This quantum mechanical effect does it affect, or does the Fermi level disappear in the Venn diagram? Or?
No, Fermi level is still there.
Okay.
Yeah. No, it does not. So basically, quantum effect, basically you can treat it as I have a larger band gap. Then that might be easier for you. So when you confine it, originally your silicon has 1.1 EV. Maybe now it becomes 1.1 plus whatever you get here, whatever you plot in the assignment. So band gap becomes larger. So the whole conduction band shift up. You can think it that way also. Right. So now, for example, this particle can only have energy E0. Then I can say that, oh, just because my ground level is here, not here. Right. Is that okay?
Yes, thank you.
Okay, great. Now, so if you look at the ultra thin body, right, UTB, there are many abbreviations. Now, what happened when you look at the mobility? Right? If we look at the thickness, when it is very thick, mobility is the same. Right? But when you get lower and lower, you will get a bump. Mobility suddenly go up. Why? You probably don't know unless you learned this before. This is because it reduces the so-called intervalley scattering. So in silicon, we're going to cover a little bit later, but I think you learn about this also, right? Silicon, it has 6 values. If we look in the K space. Right? If you don't know what I'm talking about, it's also okay. You just take it for granted. Right? I won't test you, but you do need to know that if you want to discuss with people who are in the device. Basically, in the whole reciprocal space, right, momentum space, it can have lowest energy in this 6 value. Okay, so what is mobility? Mobility is related to the scattering, right? You knock on something and then you got slow down. That's a very classical picture, right? But in addition to that, we can formulate it just like in the momentum space. We can say that it changed the momentum. So instead of saying that, okay, I run into you and then you knock me, then I go to the south by 30 degrees. That is one thing. But I also can say that I run to you with the momentum 1 unit of kx, then you bump me, and then I go to kx plus ky 45 degrees, right? That's the momentum. The same description, right, for scattering, right? So this is what is describing. And how easy it can scatter depends on many mechanisms, and the physicists already summarized them. One of them is so-called intervalley scattering. So you can have a particle that is maybe in this space. Again, this is not the real space, this is the momentum space. And then you get scattered to this space, right? Because of quantum mechanics, it's not that you can go to any space you want. You need to conserve the momentum, you need to conserve the energy, and also you need to have the appropriate phonon. But it's very easy to understand also, right? If now we are in the mechanism, I want to guess, but basically what we per unit, I mean, V equal to, so E is the gas, your probability.
The mobility to go up?
No, you lose energy immediately. In your transistor, why does it heat up? Which is VI. Can someone describe to me what is band-to-band tunneling again?
It's when the depletion width of the junction is very small, that the electron goes to the barrier due to quantum mechanics mechanism.
When it is very small, then go to tunneling. Where to where? Can you say it?
Valence to conduction.
Valence to conduction. So we have something like this, right? Then this is called band-to-band tunneling, right? Not related to this topic, okay? So we have the current, because then the electron can go down, hole will go up. So now what I'm supposed to say about is something called impact ionization. So that is what happened. Oh, you do have very tiny electron. Okay, good. Then the electron travel, right? Not much. If the
Hello everyone. This video tutorial will provide you edu. Once you are there, you should be able to find the canvas icon quiz on this Lockdown browser. Right? Once we launch, you will
the trouble. Think about if this is the cliff and you jump, you run, you drive the car, go out the cliff, and if you don't fall, isn't that you have a lot of energy compared to the fall of the ocean, the surface of the ocean? Okay. Now suddenly something happened, you fall. Good, and the band gap to create it actually, so you have hole and electron created at the same time. Think in this way: one single ID, right? This is ID, this is VD. So suddenly it comes up when the VD is high enough. Why is that? Because SOI is like this. But this is for partially depleted SOI. So here you have the depletion region, right? When you go to very, let's say 5 volts VD, what happened to this junction? It is reverse bias. So when it is high enough, you have impact ionization. Right? Yes, all of your physics you are interested and you care happen here. I only care about the current. But unfortunately, at the same time, you have something going on here. NP, impact ionization. What then happened to bulk also? But the problem is in SOI, this is floating. Right? What does it mean? It's not connected to voltage source. My writings. In SOI, right? Remember, we don't have the don't try to